Imagine a spacecraft the size of a basketball court. Its solar panels stretching over 30 meters from tip to tip, gleaming like polished silver in the absolute blackness of space. Now picture it hurling toward a planet that isn't just a world but a weapon. That's the Europa Clipper. And on October 14, 2024, from the beaches of Cape Canaveral, a Falcon Heavy roared to life. The ground shook, the sky turned white, and a 1.8 billion mile journey began before the last echoes of that launch had faded over the Atlantic. The Clipper vanished into the deep, carrying the hopes, the careers, and the $5.2 billion price tag of an entire generation of scientists. But here's what nobody said during the launch broadcast. That beautiful, fragile machine is already dead. It just doesn't know it yet. Now, let's ask the obvious question. What is the single greatest threat waiting for this robot when it reaches Jupiter? You might think it's the crushing pressure of the gas giant's atmosphere. Or maybe the violent, swirling storms big enough to swallow Earth whole. But those aren't the real killers. The real danger is something you cannot see, something you cannot touch, something that slips through solid metal like a ghost. Jupiter is not a destination. It is an environment of pure engineered hostility, a cosmic death trap designed by physics to crush, shred, and irradiate anything foolish enough to get close. From a distance, its cloud tops are beautiful, creamy whites, deep oranges, and rust-coloured bands spinning in hypnotic slow motion. A painter's dream, an artist's paradise. But beneath that paradise lies an invisible hellfire, a radiation belt that makes Chernobyl look like a warm summer breeze. A field of charged particles so intense, so relentless, that it can scramble a spacecraft's brain before the clock ticks past its first orbit. The central character of our story is not a person. It's the Clipper itself. A robot built to survive the unsurvivable. A machine designed to dance on the edge of an inferno. But here's the hard truth, the one the engineers whisper about late at night when the press conferences are over. The biggest danger facing Europa Clipper is not one single thing. It's a cascade, a chain reaction of interconnected threats, each one capable of ending the mission in an instant. The radiation belt is the primary destroyer, the ticking clock that never stops. But it doesn't work alone. It works with the cold, the distance, and the brutal physics of low-light operations. Every second the Clipper spends near Jupiter, high-energy electrons burrow into its electronics. They are not just damaging the hardware. They are creating glitches, false signals, and phantom commands. A single corrupted bit of data could tell the spacecraft to fire its thrusters at the wrong moment. A single surge of radiation could short-circuit a power system, and if the Clipper loses its orientation, if it can't tell which way is up, its antenna will miss Earth. Then it's gone. Not dead, perhaps, but floating blind and mute in a sea of radiation. Billions of dollars of science turned into a useless metal coffin. But radiation isn't the only assassin hiding in Jupiter's shadow. There's the cold. Space is cold, of course. But near Jupiter, the cold is a predator. The Clipper will fly through regions where temperatures drop to -200 degrees Celsius. Metal becomes brittle. Wiring shrinks, seals crack. And when you combine that cold with the constant bombardment of radiation, you create a perfect storm of material fatigue. The solar panels, those enormous 30-meter wings that catch the faint sunlight, are especially vulnerable. Jupiter is over 5 times farther from the Sun than Earth. The light out there is weak, incredibly weak. So the Clipper's panels must be massive to gather enough energy to run its instruments. But those same panels are also giant targets. Radiation degrades their efficiency every time the Clipper passes near the planet. Each flyby lowers the power output. Each orbit takes a piece of the mission's lifespan. It's a race. A desperate high-speed race between the radiation, slowly killing the power systems and the scientists trying to gather data before the lights go out forever. And then there's the distance. The signal from Earth takes 45 minutes to reach the Clipper. 45 minutes, That means if something goes wrong, if an alarm sounds inside the spacecraft's central computer, there is nobody to help, no engineer to hit the reset button, no technician to patch a code. The Clipper is on its own. It must make life or death decisions without human input. It has to know, by itself, when to run and hide behind Jupiter's vast magnetosphere. It has to calculate in real time whether to power down a sensitive instrument to save energy or risk everything to take one more picture of Europa's icy surface. The biggest danger, in the end, might not be a single failure. It might be the accumulation of 1,000 tiny compromises. A slightly wrong software setting, a marginally degraded circuit, a minute of delay in recognizing a problem. Each one, by itself, is harmless. But stacked together, they become an avalanche. So, here we are. This is Space, and I'm Christopher. And this is the story of a lonely machine, hundreds of millions of miles from home, accelerating toward the most dangerous place we have ever sent a robot. The countdown has already begun. The Clipper is already falling. And the radiation is waiting. We have built some of the most complex machines in human history, and we are about to launch one toward the most hostile environment in the solar system. But to understand why we are doing this, to understand what is at stake, we need to go back. We need to understand the gamble. This is not a mission that happened overnight. This is a mission that was fought for decades by people who believed, absolutely believed, that there is something beneath the ice. And they had to fight very, very hard. Let us talk about the Europa Clipper. Right now, as I speak these words, there is a spacecraft sitting in a clean room at the Kennedy Space Center in Florida. It is immense. It is the largest interplanetary spacecraft ever built by NASA. When its massive solar arrays are fully unfurled, it will stretch as wide as a basketball court. We are talking about 30.5 meters from tip to tip. Why does it need to be that big? Because Jupiter is far. The Sun is just a distant, cold campfire out there. At Jupiter's orbit, you only receive about 3 to 4% of the sunlight that we enjoy here on Earth. To generate a measly 600 watts of power, barely enough to run a few household appliances, engineers had to build the biggest solar panels ever flown on a deep space mission. 600 watts. That is all the power we have to run 9 of the most sensitive science instruments ever built. That is the technical tyranny of the outer solar system. But the size is only part of the story. The real story, the one that keeps mission managers awake at night, is the history. The Europa Clipper is the culmination of a dream that started back in the 1990s. When the Galileo spacecraft flew past Europa and sent back those incredible images of a cracked, icy surface, scientists knew something was happening. They saw chaotic terrain. They saw what looked like icebergs that had rafted into new positions. They saw a world that was geologically alive, and that meant heat, and heat meant water, and water on Earth means life. The initial concept was called the Europa Orbiter. It was supposed to launch in the early 2000s. It was cancelled. Then came the Jupiter Icy Moons Orbiter, a massive nuclear-powered flagship that would orbit all 3 of the big icy moons. It was a technological marvel on paper, but it was far too ambitious, far too expensive. It was axed in 2005. There was the Europa Explorer, the Europa Jupiter System mission. Each one died on the drawing board, killed by budget constraints, by shifting political priorities, by the sheer difficulty of the task. And then came the fight. The planetary science community, a group of people not known for being pushy, decided that enough was enough. They lobbied Congress. They wrote letters. They held town halls. There was a moment around 2014 and 2015 when it looked like this mission might die again. The budget was tight. There were those in Washington who thought that Mars was a better bet, or that we should focus on asteroids. But the scientists kept hammering the same point. Europa is the single best place in the solar system to look for life beyond Earth. It has a global ocean, more than twice the volume of all of Earth's oceans combined. It has a rocky seafloor, which likely creates hydrothermal vents, the same kind of chemical chimneys that power entire ecosystems on Earth. And it has a chaotic, dynamic surface that suggests there is energy cycling through the system. The three ingredients for life as we know it: liquid water, chemical energy, and stable conditions. Europa might have all three. We have to check. We have to know. So, after decades of paper studies, cancellations, and resurrections, the Europa Clipper was given the green light. The price tag? $5.2 billion. That is not pocket change. That is a sum that represents over 4,000 person-years of labour. That is 1,000 engineers, technicians and scientists spending a decade of their lives designing, building and testing this single machine. Every screw, every wire, every chip was agonised over. When you are spending that much money, when you are asking the American taxpayer to trust you with $5.2 billion, the pressure is immense. You cannot afford to fail. And failure out there is the mostly outcome if you do not plan perfectly. But what exactly did we buy for $5.2 billion? We bought a reconnaissance mission, and I want to be very clear about what this mission is and what it is not. The Europa Clipper is not a life detection mission. We are not going to find a little green alien in the ice. We are not going to scoop up a sample and look under a microscope. The Clipper is a scout. It is the advance guard. Its job is to answer one question: is Europa even habitable? Does it have the right chemistry? Does it have the right energy? Are there organic molecules on the surface that might come from the ocean below? To answer these questions, the spacecraft is loaded with a suite of 9 instruments that reads like a wish list from every planetary scientist in the world. There is the REASON instrument, which stands for Radar for Europa Assessment and Sounding. Ocean to near surface. This is an ice-penetrating radar. It will shoot powerful radio waves through the ice shell, which could be 10 to 30 kilometers thick. It will map the structure of the ice, looking for lakes, for pockets of liquid water, and most importantly, for the depth of the ocean itself. It will try to measure how thick the ice is, because if you ever want to land a probe on Europa, you need to know where the ice is thin enough to drill through. Then there is the MISE, the Mapping Imaging Spectrometer for Europa. This instrument splits light into hundreds of different colours like a prism. It will analyse the chemical composition of the surface. It will look for salts, for organics, for any evidence that material from the deep ocean is being brought up to the surface. There is the SUDA, the Surface Dust Analyzer. This is one of the most clever instruments on the whole spacecraft. Europa is constantly being blasted by micrometeoroids, tiny grains of dust that slam into the surface. When they hit, they eject little plumes of material. SUDA will fly through these plumes, collect the particles, and analyse them to see if they contain organic molecules. It is like catching a snowflake and tasting it to see what is in the air. There is a magnetometer to measure Jupiter's massive magnetic field and how it interacts with Europa. By measuring the magnetic induction, scientists can confirm the existence of the subsurface ocean and even estimate its salinity. There is a thermal imager, a mass spectrometer, a camera system that will map the entire surface at high resolution. We are sending the most comprehensive instrument package ever flown to the outer solar system. And all of this has to work perfectly, because we only get so many flybys. The Clipper will not orbit Europa. The radiation there is too intense. Instead, it will enter a highly elliptical orbit around Jupiter and swing past Europa between 40 and 50 times. Each flyby lasts only a few hours. Each flyby is a window, a narrow, precious window. One mistake, one instrument failure, and you lose years of data. The journey itself is a masterclass in orbital mechanics. The Europa Clipper launched in October 2024. Actually, you might be watching this after its launch, but the transit timeline is set in stone. It will fly past Mars in early 2025, using the red planet's gravity to steal a little bit of momentum. Then it will loop back around, fly past Earth in late 2026, and slingshot itself outward toward the outer solar system. The total voyage will take 5.5 years. That is a long time to wait. That is a long time for a spacecraft to sit in the silent dark, its electronics mostly sleeping, just drifting. The arrival burn, the moment it must fire its main engine to be captured by Jupiter's gravity, will happen in April 2030. That is the single most critical moment of the entire mission. If that burn fails, the Clipper will sail past Jupiter forever, a ghost ship lost in the outer dark. Why are we doing all of this? Why are we spending $5.2 billion and 20 years of effort? Because this is not just a science mission, it is the opening act. Everything about Europa Clipper is designed to pave the way for what comes next. The data we collect will be used to select a landing site for a future mission. A lander. A mission that will actually touch the surface of Europa. A mission that will drill into the ice or scoop up material and search for direct evidence of life. The Europa Clipper is the reconnaissance. It is the scout that draws the map. If it finds that the chemistry is right, if it finds that the ocean is likely habitable, then the world will be ready for the next step. And that next step will be the most profound in human history. So, think about it. $5.2 billion, 1,000 people, 20 years of dreaming, a machine the size of a bus with wings of gold. It is all riding on this one spacecraft. Every hazard it faces, every burst of radiation, every impact from a speck of dust matters. Because if the Clipper fails, we do not just lose a robot, we lose a generation of progress. We lose the best chance we have ever had to answer the oldest question. Are we alone? The radiation is waiting, the Clipper is falling, and the stakes could not be higher. We have talked about the long journey, the cold, and the hazard of high-velocity dust. But we need to be honest with you. Those threats, as serious as they are almost like the opening act. The main event, the thing that keeps mission engineers awake at night. The reason Europa Clipper carries something that looks like it belongs inside a bank vault is the radiation, and not just any radiation. We are talking about an environment so violently energetic that it will quite literally cook a spacecraft's brain if you let it. Jupiter is not just a giant ball of gas. It is a spinning magnetic dynamo of unimaginable power, and it has created a death trap around itself. This is the invisible hellfire. This is the story of why Jupiter's radiation belts are the single greatest challenge to Clipper's survival. To understand the danger, you first have to understand what you are flying into. Jupiter does not just sit there, quietly. It spins, and it spins fast, really fast. A day on Jupiter lasts just under 10 hours. Think about that. For a planet that is over 11 times wider than Earth, that is a ridiculously short day. That furious rotation is the engine that drives the whole nightmare. Deep inside Jupiter, far below the clouds we see in telescopes, the pressure and temperature become so extreme that hydrogen gas is squeezed into a liquid metal. This metallic hydrogen core is a perfect conductor of electricity. And when you have a massive, electrically conductive core rotating at breakneck speed, you get a magnetic field. Not a cute little field like the one that makes your compass needle point north. No, Jupiter's magnetic field is 19,000 times stronger than Earth's. 19,000 times. To put that in perspective, on Earth, the magnetic field extends far out into space, protecting us from the solar wind. Jupiter's field is so massive that it stretches out past the orbit of Saturn. It is the largest single structure in the solar system, and it is a trap. Here is the brutal physics. That magnetic field acts like a giant bullseye for charged particles. The sun constantly spews out a stream of high-energy particles called the solar wind. They hit Jupiter's field and get snagged. But that is just the appetizer. The main course comes from Jupiter's moon, Io. You remember Io, the volcanic moon. It is the most geologically active body in the solar system, spewing out sulfur dioxide and plasma at a rate of about a ton per second. That stuff gets ripped right off Io by Jupiter's magnetic field and gets ionized. Now you have a thick soup of charged particles, mostly electrons and protons, swirling around Jupiter, and the magnetic field does not just hold them there. It spins them. It whips them up to nearly the speed of light. These are not just particles, they are bullets. Relativistic bullets. And they are packed into a region of space that Europa Clipper has to cross over and over again. You cannot see them. You cannot feel them. But they are there, every single second, hitting the spacecraft like a machine gun. The structure of this radiation hell is not uniform. It has layers. The most intense region is the inner belt, which starts roughly at the orbit of the innermost moon, Amalthea. But that is not where Europa lives. Europa orbits further out, at a distance of about 670,000 kilometers from Jupiter's cloud tops. That puts it squarely inside the heart of the outer radiation belts. This is the sweet spot of destruction. At Europa's orbit, the radiation dosage is not measured in comfortable units. It is measured in rads. 1 rad is a unit of absorbed radiation dose. If you are a human, things get unpleasant at around 100 rads. You start feeling sick. At 300 rads, you are in serious trouble. 500 rads is widely considered the lethal dose for a human. That is the number that kills you. Death. 500 rads. At Europa's orbit, the daily radiation dose is 540,000 rads. Let that number sink in for a moment. 540,000 rads. Every day. If you, an astronaut, stepped out of a hypothetical spacecraft onto Europa's surface in an unshielded spacesuit, you would receive a lethal dose in less than 2 minutes. 2 minutes. You would be dead before you could even finish a single sentence of amazement. That is the environment we are talking about. That is not a place for life. That is a killing field. Now, the spacecraft itself is not alive, but its electronics are sensitive in a very similar way. The mission plan calls for 40 close flybys of Europa over a period of about 4 years. Each flyby, the spacecraft plunges deep into this radiation field. Over the course of the mission, the total cumulative radiation dose that the electronics will absorb is projected to be around 2.7 million rads. That is over 100 times the amount of radiation that would completely destroy most standard military-grade electronic components. We are not talking about a glitch. We are talking about total, catastrophic failure. The chips would just stop working. The computer would forget what it was doing. The navigation system would lock up. The whole spacecraft would go silent and drift off into the abyss. So the engineers had to find a way to cheat. They had to build a fortress inside the spacecraft. That fortress is called the radiation vault. The vault is not a poetic name. It is a literal box. A box weighing about 150 kilograms, built from alternating layers of titanium and aluminum. Think of it like a high-tech lasagna. Each layer is carefully chosen for its specific ability to stop different types of radiation. Aluminum is great at stopping high-energy electrons. Titanium is better at blocking protons and secondary particles created when the radiation interacts with the metal. The idea is to create a shadow. The vault casts a shadow of reduced radiation in its interior. All of Clipper's most critical electronics, the brain of the mission, are packed inside that shadow. The vault is not a perfect solution. It is a compromise. It is heavy. It takes up precious space and mass that could have been used for more scientific instruments. But it is the difference between a mission that lasts 4 years and a mission that dies in a few weeks. The vault reduces the radiation level inside to a level that the electronics can just barely survive. It is a tightrope walk. So how does radiation actually kill electronics? It is not a simple process. There are several ways it does its damage, and each one is a nightmare for engineers. First, there is ionization. A high-energy particle, like an electron fired from Jupiter's magnetic field at near light speed, slams into a silicon chip. It has so much energy that it knocks electrons loose from their atoms, creating a trail of ions. This creates tiny, unwanted electrical currents inside the chip. If enough of these particle strikes happen close together, the chip can start working incorrectly. Bits flip. A 1 becomes a 0. A calculation goes wrong. A thruster fires when it should not. This is called a single event upset. It is like a small stroke in the spacecraft's brain. Normally, you can recover from these by resetting the system. But in this environment, the upsets happen so frequently that the computer might spend all its time just trying to fix itself. Then there is displacement damage. This is more insidious. A heavy particle, like a proton, hits a silicon atom and physically knocks it out of its lattice position. The crystal structure of the semiconductor is damaged. Over time, these defects accumulate. The efficiency of the chip degrades. Transistors become slower. They need more voltage to switch on. Eventually, they just stop working. It is a slow, creeping death. The chip does not die all at once. It gets dumber and slower until it cannot do its job anymore. This is the kind of damage you cannot reset. It is permanent. And then there is the big one, the single event latch-up. This is a nightmare scenario. A single particle strike can trigger a parasitic transistor inside the chip to switch on. This creates a short circuit that draws huge amounts of current. If not stopped immediately, the chip will literally overheat and melt. The spacecraft has to detect this and cut power to the affected system in microseconds, then turn it back on. It is a cardiac arrest for the electronics. The engineers have designed protection circuits to handle this, but it is a constant danger. One unlucky strike, and you lose a critical component forever. To make sure the Clipper could handle this onslaught, the engineers did not just run computer simulations. They tortured the components. They took commercial off-the-shelf chips, the same kind you might find in a consumer laptop, and put them in a particle accelerator at the Massachusetts Institute of Technology and at the Goddard Space Flight Center. They blasted these chips with focused beams of protons and electrons. They simulated years of radiation exposure in just a few hours. The results were sobering. The commercial chips failed. Some failed in minutes. They could not handle the abuse. So the team had to go with radiation-hardened parts. These are not your typical chips. They are built on specialized manufacturing processes like silicon on insulator or Y. In a SY chip, the active silicon layer is isolated from the substrate by a layer of insulating material. This reduces the amount of current leakage from particle strikes. It is slower. It is more expensive. It is less powerful than the latest consumer chips, but it survives. That is the only thing that matters. Clipper's computer is not a racehorse. It is a mule. It is slow, tough, and built to keep going long after a faster machine would have given up. But even with the volt and the hardened parts, the mission is not invincible. This is where the concept of graceful degradation comes in. The engineers know that they cannot stop the radiation forever. They can only slow it down. Over the 4 years of the science phase, the electronics will degrade. It is inevitable. Components will start to fail. The camera might get noisier. The spectrometer might lose some sensitivity. The computer might need more frequent resets. The mission has to complete its primary objectives before the damage becomes too severe to continue. It is a race against time. Every flyby ages the spacecraft a little more. Every particle hit brings it a step closer to the end. The Clipper is not built to last forever. It is built to last just long enough. It is built to take the beating, gather the data, and send it home before the invisible hellfire finally wins. And that is a very real possibility. Because at the end of the day, Jupiter's radiation belts are a force of nature. They are relentless. They are unforgiving. And they are waiting. The engineers at the Johns Hopkins Applied Physics Laboratory, where the Europa Clipper was designed and built, understood this grim calculus from the very beginning. They knew that the spacecraft was essentially a suicide machine. It would fly to Europa, take a beating, and die. The only question was whether it could gather enough science before the radiation killed it. To maximize that window, they had to think about things that most spacecraft engineers never worry about. For example, the orientation of the spacecraft during its orbit matters enormously. The vault is not a perfect sphere of protection. It is a box. It shields what is inside it, but only if the spacecraft is oriented correctly. The engineers have to plan the entire trajectory of the mission to keep the vault pointed towards the worst of the radiation, like a soldier holding a shield against incoming fire. If Clipper were to tumble, even for a few minutes, with the wrong side facing Jupiter, the radiation could sneak in through a less protected seam and fry a critical subsystem. This leads to a deeply practical problem. The spacecraft cannot afford to make a mistake. Every navigation burn, every maneuver, every turn of the camera has to be carefully calculated to avoid exposing the vulnerable components. The onboard computer has a fail-safe mode, called safe mode, that is designed to orient the spacecraft to the Sun and wait for commands from Earth. But in Jupiter's radiation environment, safe mode could actually be a death sentence. If the spacecraft loses its sense of direction and tries to point its solar panels at the Sun, it might accidentally point its unprotected side straight at Jupiter and absorb a lethal dose of radiation before ground control can intervene. The engineers have had to write special software for Clipper that overrides the standard safe mode behavior. If the spacecraft senses that it is in a high radiation region, it will deliberately ignore the Sun and keep its vault pointed at Jupiter, even if that means its solar panels are not fully illuminated. It is better to run low on power for a while than to die of radiation poisoning. The historical context of this struggle is important. The first spacecraft to brave Jupiter's radiation was Pioneer 10 in 1973. It was a brave little probe, but it had no radiation vault. Its electronics were simple, discrete components, not complex integrated circuits. It survived the flyby, but its instruments suffered. The camera, for instance, produced images that were degraded by noise. Pioneer 11, which followed in 1974, did slightly better, but the radiation still caused problems. Then came Voyager 1 and 2. They had better shielding, but still nowhere near enough to handle a long-term mission. They were flyby missions, passing through the worst of the radiation in just a few hours. They survived. But their electronics aged noticeably. The Voyagers were tough, but they were not built for prolonged exposure. The real wake-up call came with the Galileo mission, which orbited Jupiter from 1995 to 2003. Galileo had a tape recorder that stored its data. The radiation was so intense that the tape recorder failed multiple times. The mission operators had to constantly intervene to reset it. At one point, the spacecraft's star scanner, used for navigation, failed because radiation had damaged its detector. Galileo became partially blind. It had to rely on gyroscopes and ground-based tracking to know where it was pointing. The spacecraft also experienced a total of 8 anomalies during its mission that were directly attributed to radiation strikes. These were not minor glitches. They were major events that could have ended the mission. The lesson from Galileo was brutal and clear. If you want to survive around Jupiter, you cannot just hope for the best. You have to engineer for the worst. You have to build a fortress, and yet, even as we have improved our materials and designs, Jupiter has not gotten any weaker. In fact, the radiation environment has been measured more precisely by later missions like Juno, which arrived in 2016. Juno is in a polar orbit, which keeps it far from the worst of the radiation belts for most of its orbit. But even so, Juno carries a radiation vault made of titanium. It has survived years in orbit, but its own instruments are gradually degrading. The JunoCam, a public outreach camera, has developed so many radiation-induced artifacts that its images look like they were taken through a dirty window. The star trackers, used for navigation, have had to be reprogrammed multiple times because the radiation was causing them to see false stars. Juno is limping along, but it is a testament to the difficulty of operating in that environment. Clipper, with its 40 flybees through the heart of the radiation belt, will face a much greater challenge. So what happens when the radiation finally wins? It will not be sudden. There will be no explosion, no dramatic failure. The spacecraft will simply become slower, more confused. The computer will crash more often. The instruments will produce noisier data. The navigation system will start to drift. Eventually, a single unlucky particle strike will trigger a latch-up in a critical component that the protection circuits cannot clear. Or the cumulative displacement damage will push a voltage regulator past its tolerance. The spacecraft will lock itself into a safe mode that it cannot recover from. The radio signal from Earth will go unanswered. The Clipper will fall silent, a ghost in Jupiter's shadow. It will continue to orbit, a dead hunk of metal and circuit boards, still plunging through the radiation fields, still being peppered by particles, until its orbit decays, and it plunges into Jupiter's atmosphere, or its components are so degraded that they physically crumble. But not before it sends home the data. That is the deal. That is the trade. The Clipper is a messenger. It will sacrifice itself so that we can learn. It will endure the invisible hellfire so that we can see Europa's surface, measure its ice shell, taste its potential ocean, and maybe, just maybe, find evidence that we are not alone in this cold, dark universe. The radiation is the price, and the Clipper is willing to pay it. The price of admission to the Jovian system is high, but the engineers who built the Europa Clipper didn't just write a check and hope for the best. They built a fortress, not a fortress of stone or steel, but a fortress of geometry and material science. A shielded vault that sits at the very heart of the spacecraft, and it is the single most important piece of engineering on this entire mission. You see, the problem with radiation isn't just that it's energetic, it's that it's sneaky, it's clever. And if you try to block it with the wrong stuff, you can actually make the problem worse. Let's talk about that vault. It's a box roughly the size of a small SUV's cargo area, weighing in at about 150 kilograms, which is a lot of mass to dedicate to nothing but shielding. But that mass is absolutely non-negotiable. The walls of this vault are not a simple slab of metal. They are a layered sandwich, a carefully engineered stack of materials designed to fight a two-front war. The outer layer, the first thing the radiation hits, is a thin sheet of titanium. Titanium is a high atomic number material, which means it is very good at stopping electrons. When a high-energy electron slams into a titanium atom, it dumps its energy and stops. Problem solved, right? Not exactly. Because here's the devilish detail. When you stop an electron, you don't just make it disappear. You create a new kind of monster. When that super-fast electron decelerates violently, it gives off a photon, a high-energy X-ray. This is called Bremsstrahlung radiation, from the German words for braking radiation. It's the flash of light you get when you slam on the cosmic brakes. So if you used a thick slab of aluminum instead of titanium, you'd stop some electrons, but a huge number of them would just pass right through, and then start shedding their energy inside the spacecraft, creating a shower of secondary X-rays that are even harder to stop than the original electrons. It's like trying to stop a wave by throwing a rock into it. You just make more ripples. That is why the vault uses a two-layer system. The titanium is thin, just a few millimeters thick. It stops the primary electrons cold, absorbing them and converting their energy into heat. But then, the titanium also generates that secondary X-ray shower. And this is where the aluminum comes in. Behind the titanium is a much thicker layer of aluminum. Aluminum is terrible at stopping high-energy electrons, but it is surprisingly good at absorbing these secondary X-rays. The aluminum acts like a sponge for the Bremsstrahlung radiation. So the titanium is the bouncer at the door who stops the troublemaker. But the aluminum is the cleanup crew that mops up the mess the bouncer creates. Without that aluminum layer, the inside of the vault would be flooded with killer X-rays, and the electronics would be fried in weeks. Now, inside that vault, it's a tight squeeze. you have the main flight computer, the brain of the whole operation. Sitting right next to it is the power distribution unit, the heart that pumps electricity to every system. And packed into the remaining space are the instrument controllers, the little nervous systems for each of the 9 science instruments. These are the components that absolutely, positively cannot fail. The instruments themselves, the cameras, the spectrometers, the ice-penetrating radar antennas have to live outside the vault. They are exposed to the full, unfiltered fury of Jupiter's radiation belts. Some of them will degrade. Some of them will accumulate damage. But their brains, their control electronics, are tucked safely inside this metal sanctuary. That is the fundamental trade-off. The sensors are sacrificial. The brains are protected. But here's the second paradox. A box designed to keep radiation out also has to keep heat in, and keep heat out, and it has to do both at the same time. Think about it. The vault is essentially a thick metal box in a vacuum. Space on one side is minuscule, hundreds of degrees below zero. On the other side, the electronics inside are generating heat. If the vault is too thermally conductive, if it sucks the heat away too efficiently, the electronics will freeze solid at cold temperatures. If it's too insulating, if it traps the heat inside, the electronics will cook themselves to death at hot temperatures. The temperature inside that vault has to stay stable. It has to stay around a comfortable 20 degrees Celsius, plus or minus a few degrees, for the entire multi-year mission. That is a brutally difficult thermal balancing act. The solution is a system of heat pipes. These are not simple copper wires. They are sealed tubes containing a tiny amount of fluid, typically ammonia. When the electronics inside the vault get hot, that heat boils the liquid ammonia at the hot end of the pipe. The vapor shoots to the cold end, which is outside the vault, where it condenses back into a liquid and releases its heat into space. Then the liquid wicks back to the hot end through a porous lining, and the cycle repeats endlessly. It's a passive, self-regulating system. No moving parts, no pumps to fail. These heat pipes are designed to extract about 600 watts of waste heat from the vault, about the same as a good microwave oven running on high. They pull that heat out and dump it into space, keeping the electronics right at that perfect 20 degrees. If the vault gets too cold, the heat pipes just slow down. If it gets too hot, they speed up. It is a beautiful, simple, mechanical organism. But even with all this protection, the vault is not a perfect shield. Some radiation gets through. It's inevitable. High-energy protons, the most penetrating particles in Jupiter's belts, can punch right through 4 centimeters of aluminum. They don't care about your sandwich. They just go. And when a proton hits a single memory cell in the flight computer's RAM, it can do something terrifying. It can flip a bit. It can turn a 0 into a 1 or a 1 into a 0. That is called a single event upset. A bit flip. And in a spacecraft that is executing millions of calculations per second, a single flipped bit in the wrong place could be catastrophic. It could tell the thrusters to fire at the wrong time. It could tell the antenna to point away from Earth. It could corrupt the data from an instrument. It's the digital equivalent of a cosmic sneeze. So the engineers had to build a computer that is smart enough to catch its own mistakes. Every critical piece of memory in the Europa Clipper uses a technique called triple modular redundancy. That means there are not 1, not 2, but 3 exact copies of every critical piece of data stored in 3 separate memory banks. When the computer needs to read a value, it reads all 3 copies. If 2 say 1 and 1 says 0, the computer knows the 0 is the error, and it uses the value from the 2 that agree. A majority vote. This works incredibly well, but it is not enough. On top of that, the computer uses error-correcting code memory, or ECC memory. This is a mathematical trick that allows the computer to detect when a single bit has been flipped and automatically correct it. In most cases, you won't even notice. The computer just fixes the error and moves on as if nothing happened. For double bit errors, the computer detects them and halts the operation, preventing corruption. And the software is hardened against crashes, just as hard as the hardware is hardened against radiation. Every single command that the computer sends to any subsystem is first verified by a separate validation circuit. The computer doesn't just fire a thruster because a bit flickered. It sends the command. The command is checked against a pre-approved template, and only then is it executed. If the command doesn't match the template, it is rejected. And if the computer does crash, if it gets hit by a heavy proton that scrambles its brain, the fault protection system is designed to reboot the entire computer in less than 10 seconds. 10 seconds of silence, 10 seconds of drift. Then the computer comes back online, loads its pristine, uncorrupted boot code from protected read-only memory, and resumes operations as if nothing happened. Now, let's be brutally honest. Even with all of this, even with the vault, with the titanium and aluminum sandwich, with the heat pipes, with the triple redundant memory, with the error-correcting code, and with the fast reboot software, no single component on the Europa Clipper is guaranteed to survive the full mission. This is not a statement of failure. It is a statement of hard reality. The engineers knew they could not build an indestructible spacecraft. Instead, they had to accept a certain probability of component failure. They had to do risk analysis. They had to say, okay, we think this power converter has an 80% chance of surviving the full mission. That is not good enough. So they put 3 of them in. 3 independent power converters, each one capable of delivering the full electrical power the spacecraft needs. If one fails, the other 2 pick up the slack. If 2 fail, the last one still gets you home. There are 2 identical flight computers, sitting side by side, hot swappable. If the primary computer has a fatal crash, the backup takes over in milliseconds. There are 2 star trackers, 2 sets of gyroscopes, 2 of almost everything that moves. It is a philosophy of graceful degradation. The Clipper will get broken. It is a guarantee, but the engineers designed it to break in a way that still allows it to complete its primary mission. It will lose bits. It will lose components. It will accumulate damage. But it will keep flying. It will keep gathering data. It will keep sending it home. The radiation is the enemy, but it is a predictable enemy, and the Clipper is built to survive that predictability, even when the odds are not in its favour. It is a machine designed to accept scars. The orbital dance. Why, Europa Clipper never orbits Europa. In the grand theatre of space exploration, the most brilliant moves are often the most counterintuitive. The Europa Clipper, this magnificent piece of human engineering, will spend years studying one of the most tantalizing worlds in our solar system. Yet it will never, ever orbit it. It sounds almost absurd, doesn't it? You send a spacecraft all the way to Jupiter, to the doorstep of this frozen moon with its hidden ocean, and you decide not to settle in for a nice long stay in orbit around it. But that decision, that deliberate choice to keep this spacecraft dancing at arm's length, is quite literally the difference between a triumphant mission and a silent, fried piece of junk drifting through the void. Let us pull back the curtain on why. The number one reason, the monster under the bed, is radiation. Jupiter doesn't just have a magnetic field, it has a magnetic cage of pure, unadulterated fury. It traps charged particles, electrons, and protons, accelerating them to near-light speed. This creates radiation belts that make anything inside Chernobyl's reactor core look like a gentle spring rain. If you put the Europa Clipper into a stable orbit around Europa, a nice, cosy, predictable orbit, where it could just hang out and take its sweet time mapping the surface, you would be signing its death warrant. The spacecraft would be constantly bathed in this hellfire. Every second it spent in that orbit, the radiation dose would accumulate. We are not talking about years of operation here. We are talking about weeks. Within a few weeks, the cumulative dose would fry the delicate electronics, blind the sensors, and turn a billion-dollar mission into a drifting, silent tombstone. The radiation environment near Europa is so harsh that it is measured in megarads, millions of times the lethal dose for a human. And electronics, while tougher than flesh and blood, have their limits. A constant Europa orbit means guaranteed, rapid, catastrophic failure. So, what does a clever mission designer do? They cheat. They play the geometry. Instead of orbiting Europa, the Clipper will orbit Jupiter in a long, looping, highly elliptical path. Think of it like a boxer in the ring. You don't stand toe-to-toe with the heavyweight champion and trade punches. You jab, you dance, you step in and out of range. That is exactly what the Clipper does. It stays mostly far away from the radiation danger zone, orbiting Jupiter at a safe distance. But once every few weeks, it swoops in for a lightning-fast flyby of Europa. These flybys are the jabs. They last only a few hours, sometimes just a precious few minutes at the closest point. The spacecraft dives down, screaming past the surface at incredible speed, gathering all the data it can, and then it immediately retreats back into the safety of the outer orbit. It's a hit-and-run strategy, a guerrilla warfare tactic applied to planetary science. It is the only way to survive. But getting these flybys just right, that takes a masterclass in orbital mechanics. The Clipper doesn't just aim at Europa and hope for the best. It uses the other giant moons of Jupiter as celestial billiard balls. Ganymede and Callisto, those massive Galilean satellites, act as gravitational slingshots. The Clipper will fly by Ganymede, and the moon's gravity will bend the spacecraft's trajectory, speeding it up, slowing it down, or changing its angle. It will use Callisto in the same way. Over the 4-year science phase, the mission team will choreograph a complex sequence of dozens of these flybys of the other moons, each one carefully sculpting the orbit to set up the next Europa encounter. It is a delicate, intricate dance across a gravitational chessboard, where one miscalculation could send the spacecraft spinning off into empty space, or, worse, crashing into the icy surface. This is not a simple commute. It is a perfectly timed series of cosmic slingshots, and the timing must be perfect, down to the second. It is not enough to just fly by Europa. You have to fly by Europa at the right moment. Jupiter's magnetic field is not a static bubble. It rotates with the planet, spinning once every 10 hours. This means the radiation belts are not uniform. They are twisted and warped, like the stripes on a barber pole. The radiation intensity around Europa changes dramatically depending on where Europa is located relative to this rotating field. The flybys are scheduled during what the team calls the safe windows. These are the moments when the magnetic field lines are most favourable, when the spacecraft can dip into the danger zone for the shortest possible time, and avoid the absolute worst of the radiation torrent. It's the geometry of survival. Every single flyby is timed to occur when Europa is at a specific longitude relative to Jupiter, ensuring that the Clipper is in the least harmful slice of the radiation environment. If the timing is off by even a few minutes, the radiation exposure could double or triple, pushing the spacecraft past its limits. Now, let's talk speed. When the Clipper makes its closest approach, it will be absolutely hauling. It will fly as low as 25 kilometers above the surface. 25 kilometers. That is lower than a commercial jetliner flies above Earth. At that altitude, you could see individual cracks in the ice, the chaotic terrain, the reddish-brown stains of organic material. But the spacecraft is moving at a velocity of 4 kilometers per second. That is 9,000 miles per hour. At that speed, you could fly from New York to Los Angeles in under 10 minutes. The entire diameter of Europa is only 1,900 kilometers. At the Clipper's speed, it will cover that distance in less than 8 minutes. It is a full sprint past a world. The science instruments, all the cameras, spectrometers, radar and magnetometers must be pre-programmed to operate on a rigid, automated schedule. As the spacecraft approaches, the instruments wake up. As it dives over the surface, they take their measurements, snapping images, reading the ice composition, listening for magnetic whispers of the ocean below. And then, before the spacecraft even leaves the moon's shadow, the instruments must stow away. There is no time for a second pass. It is one shot, one chance, and it is over in a blur of ice and radiation. What makes all of this even more nerve-wracking is the autonomy. Earth is on average 45 light minutes away from Jupiter. That means any command you send from mission control takes 45 minutes to reach the spacecraft, and any response takes another 45 minutes to come back. Round trip, you are waiting an hour and a half just to hear your own hello. When the Clipper is screaming past Europa at 9,000 miles per hour, there is no time for that conversation. The entire flyby sequence, every single command to every instrument, every adjustment of the attitude control thrusters, every management of power from the solar panels to the batteries, must be executed by the spacecraft itself. It has to think for itself. It has to know when to point its high-gain antenna away from Earth and towards the moon. It has to know when to fire its thrusters to keep the instruments locked on target. It has to know that if a sensor overheats, it has to shut it down. All of this autonomy happens without any human help, with the mission team back on Earth just watching the data come in 45 minutes later, holding their breath. It is a strange feeling to build a machine that you cannot truly control in the moment, only trust. And here is the crushing reality of this orbital dance. You cannot miss a flyby. If something goes wrong, if a computer glitch or a software hiccup causes the spacecraft to miss its target by even a few seconds, that opportunity is gone forever. The orbital geometry is constantly shifting. The positions of Europa, Ganymede, and Callisto are always changing. You cannot just swing back around and try again next week. The alignment of the moons and the safe windows in the magnetic field will not repeat exactly for years, maybe decades. A missed flyby is a lost science target, a blank page in our understanding of that world. There is no plan B for that specific encounter. The entire mission is a high-wire act, a cascade of precisely timed events where failure at any point could derail years of planning. The pressure on the navigation team, on the engineers, on the scientists, is immense, and yet the Clipper is built for this. It is built to accept those scars, to endure the hits, and to keep dancing. Because that dance, that frantic, dangerous, beautiful orbital ballet, is the only way we can get close enough to touch the secrets of Europa's ocean without being burned alive by the fury of Jupiter. It is a compromise between curiosity and survival, and it is an absolute work of celestial art. Jupiter's gravity, the invisible killer. And so, with the radiation belts conquered in our minds, at least for the moment we turn our attention to the second great threat. A threat that is invisible, silent, and utterly unavoidable. It is the gravitational field of Jupiter itself. The most powerful gravitational well in the entire solar system, a force so immense that it tugs at the very fabric of space-time around it. You might think of gravity as a simple, static thing, a gentle pull like the one that keeps your feet on the ground. But Jupiter's gravity is not static. It is a dynamic, time-varying source of chaos. It is a living, breathing monster that shifts and flexes as its many moons dance around it. And our little spacecraft, the Europa Clipper, has to navigate through this monster's lair without getting swallowed whole. Let's be clear about what we're dealing with here. This isn't just a matter of pointing the spacecraft and firing the engines. The trajectory the Clipper must follow is a tightrope walk across an abyss. The spacecraft has to thread a needle, a very specific, very narrow path between Jupiter's massive gravity well and the absolute necessity of avoiding excessive delta V. Delta V, for those of you who don't speak rocket scientist, is the change in velocity. It's the currency of space travel, and Clipper has a limited budget. We cannot just slam on the brakes when we get to Jupiter. We don't have the fuel for a huge retro burn. That would require a spacecraft the size of a skyscraper, and we just don't have that kind of money or rocket power. think about the approach itself. The Clipper will be screaming toward Jupiter at an interplanetary cruise velocity of roughly 15 kilometers per second relative to Jupiter. That's over 33,000 miles per hour. That's fast enough to cross the continental United States in under 5 minutes. Now, to get into orbit, the spacecraft has to slow down from that insane speed to a reasonable bound orbit. And how do we do it with no fuel? We use gravity assists. We use the gravity of Jupiter's own moons, specifically Ganymede and Callisto, as natural braking pads. We slingshot around them, stealing just a tiny bit of their orbital energy to shed our own velocity. It's a beautiful, elegant solution, but it is also terrifyingly precise. If the initial Jupiter orbit insertion burn in 2030 fails, if something goes wrong with the engine or the timing is off by even a fraction of a second, the mission is over before it begins. The spacecraft will simply fly past Jupiter on a hyperbolic escape trajectory, using the giant planet's gravity to hurl itself out of the solar system forever. No do-overs, no second chances, just a lonely, silent spacecraft drifting into the darkness because it missed its one and only chance to slow down. But even if the initial insertion works perfectly, the real challenge is just beginning. This is where the resonant orbits come into play, and they are both our greatest tool and our greatest vulnerability. The Clipper doesn't just float around Jupiter in a lazy circle. It uses a series of carefully designed passages that are in a specific resonance with the moons of Ganymede and Callisto. We're talking about orbital resonances like a 2-to-1 or 3-to-1 ratio. What that means is that the Clipper completes 2 orbits of Jupiter for every 1 orbit of Callisto, or 3 orbits for every 1 orbit of Ganymede. These resonances create predictable patterns. They are like a metronome, a steady, predictable beat that we can rely on to swing us past Europa time and time again. But here's the killer. These resonances also amplify tiny errors exponentially. They act like a magnifying glass for any imperfection in our trajectory. A miscalculation of just a few meters per second in a trajectory correction maneuver, a tiny error so small it's barely measurable, could be amplified over multiple orbits until the spacecraft is sent into a decay spiral. A death spiral, if you will. It could send Clipper plunging inward toward Jupiter's crushing atmosphere. And folks, Jupiter's atmosphere is not like Earth's. It's a thick, turbulent, high-pressure hell of hydrogen and helium with winds that blow at hundreds of miles per hour. If Clipper goes in there, it is crushed, melted, and vaporized in seconds. There's no surviving that. And let's not forget the tidal forces. As the Clipper swings close to Europa, and I mean really close, sometimes just 25 kilometers above the surface, Jupiter's gravity gradient becomes a physical, tangible threat. It's not just a force that pulls the spacecraft toward the planet. It's a force that stretches and compresses the spacecraft's structure itself. Imagine holding a rubber band between your 2 hands and pulling it apart gently. That's what Jupiter's gravity does to the Clipper, but with a lot more force. The side of the spacecraft closest to Jupiter feels a stronger pull than the side farthest away. And this difference, this gradient, creates a stretching effect. And as the spacecraft rotates and swings around, this stretch becomes a cycle of axial compression and tension. The spacecraft is literally being flexed, over and over again, like a piece of metal being bent back and forth until it snaps. The solar panels, which are a massive 30.5 meters across, from tip to tip, experience these bending moments directly. They are long, thin, and incredibly fragile. Every time Clipper passes Europa, those solar panels are subjected to a nasty twisting force from the tidal gradient. Over the course of the mission, which is designed for over 40 flybies, this can cause material fatigue. Tiny micro cracks can form in the joints and the support structures. The panels can start to warp. The electrical connections can break. It's a slow, insidious form of damage. It's death by 1,000 tiny stretches. This is not theoretical, by the way. We have seen what happens to spacecraft around Jupiter. We have a historical precedent, and it is a grim one. The Galileo mission, NASA's first dedicated orbiter of Jupiter, spent 8 years in the Jovian system from 1995 to 2003. It collected a mountain of data, revolutionized our understanding of the moons, and proved that the Europa Clipper concept was even possible. But Galileo also had an end-of-life plan. The mission planners knew that if the spacecraft died and drifted uncontrollably, it could eventually crash into Europa, and if it crashed into Europa, it could contaminate that pristine ocean with hardy Earth bacteria that had hitched a ride from our planet. That would be a scientific catastrophe. It would ruin any chance we had of finding native, pristine life. So, they made a tough decision. They deliberately crashed Galileo into Jupiter's atmosphere. They steered it on a collision course with the gas giant, sacrificing the spacecraft in a controlled, noble death to protect the very moon it had studied for so long. The spacecraft burned up in Jupiter's atmosphere, carrying its secrets and its earthly microbes to a fiery end. It was a necessary mercy killing. The Europa Clipper's end-of-life plan is exactly the same. After the science phase is complete, after the Clipper has made its last daring flyby of Europa and sent back its final data, the spacecraft's fate is sealed. It will be guided on a controlled impact into Jupiter's atmosphere. It will be a final, definitive act of planetary protection. We don't want to leave any loose ends. We don't want our own legacy to be the accidental contamination of the most promising world for life in our solar system. So, the Clipper will be flown into the crushing atmospheric oven of Jupiter. It will be vaporized, turned into a shower of superhot plasma, and that will be that. No graveyard orbit, no drifting junk, just a clean, final, necessary end. It is a sobering thought, isn't it? That we design these brilliant, beautiful machines. We send them across hundreds of millions of miles of empty space. We ask them to perform miracles of engineering, and then, when their work is done, we deliberately destroy them. But it is the price we pay for knowledge. It is the price we pay for being responsible explorers. And that journey, from the radiation belt to the gravity well to the tidal flexing to the final fiery plunge, is the story of Europa Clipper. It is a story of survival, of precision, and of a quiet, determined sacrifice. And it is far from over. So we have talked about radiation, that invisible, relentless storm. We have talked about gravity, the silent, crushing hand that pulls and strains. But now, we need to talk about the brute force, the cosmic shotgun blast. Because Jupiter does not just poison you with energy or break you with pressure. It also shoots at you. The danger here is not a theory. It is a physical fact of the environment. Jupiter is the biggest gravitational anchor in the solar system, outside of the Sun itself. It is a titan, and like any titan, it attracts attention. Comets from the deep freeze of the Oort cloud, asteroids from the main belt, and just plain old interplanetary dust. Everything that drifts close enough gets pulled in. It is like a cosmic vacuum cleaner, except the debris does not just get sucked up neatly. It gets accelerated, it gets focused, and it gets dangerous. Now, think about where we are going. The inner Jovian system is not a clean, empty void. It is a messy, crowded, and frankly violent neighbourhood. The region near the orbits of Io and Europa is a debris field. Io, that tortured moon, is the most volcanically active body in the solar system. It is constantly spewing plumes of sulfur and rock into space. That material does not just float away and disappear. It hangs around, forming a thin, tenuous cloud of particles that the Clipper has to fly through. And then you have the small inner moons Metis and Adrastea. They are tiny, barely more than rubble piles, but they are battered. Bits of them get knocked off by impacts, and that debris forms a faint ring, a dusty halo that Europa itself orbits right through. So the spacecraft is not flying through a pristine vacuum. It is flying through a shooting gallery, and the bullets are small, very small, but do not let the size fool you. A grain of dust, just 1 millimeter across. about the size of a grain of sand, hitting the Clipper at a relative speed of 4 kilometers per second. That is not a gentle tap, that is a violent impact. That tiny grain carries the same kinetic energy as a 5.56mm NATO rifle round. A bullet fired from an assault rifle. Now imagine that bullet hitting your car or your house. It would punch a hole. It would do damage. And the Clipper is going to be hit by these things repeatedly for years. The biggest target on the spacecraft, the part that sticks out and catches the sun and the wind and the dust, is the solar array. Those huge wings, each one the size of a basketball court, are essential for power. They are also, from a debris perspective, a giant bullseye, so the engineers spent a lot of time thinking about this. They simulated thousands of impact scenarios. They shot tiny projectiles at test panels at ridiculous speeds to see what would happen. What they found is that the honeycomb panel structure is tough. It can survive a few small holes. A tiny hole in the substrate is not the end of the world. But a direct hit on a solar cell string is a different story. Each of those massive panels is made up of about 6,000 individual solar cells. They are wired together in strings, like a chain of lights. If one cell gets shattered by an impact, it can short out the entire string. That is a lot of lost power, all at once. The mission has some margin built in. The spacecraft can afford to lose up to 10% of its cells. That is about 600 cells per panel. 600 bullet holes before things start getting critical. That sounds like a lot, but remember, we are talking about a multi-year mission in a debris field. It is not a matter of if they will get hit, but how many times. So how do you build a panel to survive a cosmic sandblasting? You build it like armour. The base is a Kapton substrate, a tough, heat-resistant plastic film that sits on a frame made of carbon fibre reinforced aluminum, which is incredibly strong and light. And then, on the very front facing the source of the impacts, there is a sacrificial outer layer. This layer is designed to take the hit. It absorbs the energy of the tiny particle, shattering itself in the process. So the actual solar cell underneath has a better chance of surviving. But the cleverest part is not the armour, it is the wiring. Each individual solar cell has a bypass diode. This is a tiny electrical component, a one-way gate for electricity. If a cell gets damaged and shorts out, the diode kicks in. It reroutes the current around the broken cell, isolating it from the rest of the string. It is a self-healing mechanism. The string loses one cell, but the rest of them keep working. It is a brilliant, elegant solution to a problem that would otherwise cripple the power system. And it is not just the solar panels. The spacecraft has eyes too. The star trackers are optical cameras that look at the stars to figure out exactly where the Clipper is pointing. If a dust grain scratches the lens or cracks the glass, the tracker could get confused. The spacecraft could get lost. So the engineers put a sapphire window over the camera. Sapphire is incredibly hard, second only to diamond. It can resist impacts that would shatter ordinary glass. It is not invincible, but it gives the system a fighting chance. Now here is a thought that keeps some engineers up at night. We worry about natural debris, the volcanic ash from Io, the dust from the rings. But there is another source. Human activity. We have put a lot of stuff in space around Earth, and we are starting to put stuff everywhere. The Clipper, however, carries no propellant for debris avoidance. This is not a car with brakes and a steering wheel. It is a bullet. It has one trajectory. It must simply fly through whatever is there and survive. There is no dodging. There is no swerving. There is only the path, and the hope that the armour is strong enough, and the diodes are fast enough. It is a sobering thought. We are sending this incredibly complex piece of human ingenuity into a place where it will be shot at every day for years. And we just have to trust that we built it right. That is the reality of exploration. You design for the worst, you hope for the best, and you accept that the universe is not a friendly place. It is dangerous, it is messy, and it is absolutely beautiful. And so, having survived the launch, having unfurled its delicate instruments, trusting in every weld and wire, Europa Clipper now has to face its first constant and utterly unforgiving challenge: the sun, or, more accurately, the lack of it. We have to talk about the solar panels, because this is where the engineering stops being about clever gadgets and starts being about a fundamental, almost primal fight for survival. You see, out here in the inner solar system, we take the sun for granted. It's warm, it's bright, it powers everything. But Jupiter is a very different neighbourhood. Jupiter sits at a distance of roughly 5.2 astronomical units from the Sun. That is 5 times farther out than we are. And here is the thing about light: it follows the inverse square law. It sounds like a boring rule from a physics textbook, but in reality, it is a brutal mathematical truth. If you double the distance from the Sun, the light is not half as bright. It is 1/4 as bright. So at Jupiter's orbit, the sunlight is not just a little dimmer, it is 25 times weaker than what we feel on a sunny day on Earth. 25 times. Imagine trying to read a book under a street lamp that is a 1/4 mile away. That is the energy budget Clipper has to work with. And yet, this spacecraft needs power. Not just a little trickle of electricity to keep a clock ticking. It needs serious, heavy-duty power to run its radar, its spectrometers, its cameras, its computers, its heaters, and its radio. The mission requires about 600 watts of continuous power. 600 watts. That is roughly the power draw of a small microwave oven, for a spacecraft that cost billions of dollars. Think about that. We are sending a robot across 500 million miles of empty space, and the entire operation, the entire scientific treasure hunt, hinges on the same amount of energy it takes to heat up your leftover pizza. The margin for error is razor thin. So how do you squeeze 600 watts out of sunlight that is barely a whisper? You build the biggest damn solar panels ever flown. And I mean that, literally. When fully deployed, Europa Clipper measures 30.5 meters from tip to tip. That is longer than a basketball court. It is the largest set of solar arrays ever installed on a planetary spacecraft. And they have to be that big because the math demands it. You cannot cheat physics. You just have to build a bigger net. But here is the nightmare scenario, every engineer's worst dream. Those panels have to get from Earth to Jupiter, folded up like a deck of cards. They are launched in a tight, compact stack, strapped down with explosive bolts. It is a beautiful, terrifying arrangement of carbon fibre, Kapton film, and thousands of solar cells, all compressed into a volume that can fit inside a rocket fairing. Then, after launch, after the spacecraft has settled into its cruise trajectory, the command goes out: fire the bolts. And then, you wait. The deployment is not a quick flick of a switch. It is a slow, deliberate, agonizing process. A spring mechanism pushes each panel out, one segment at a time. It takes about 45 minutes to deploy a single panel. 45 minutes of holding your breath. And because there are 2 panels, you are looking at nearly an hour and a half of sheer anxiety for the team back on Earth, staring at telemetry data, watching voltages slowly rise. If a hinge is stuck, if a motor seizes, if a sensor gives a false reading, if a single hold-down bolt fails to release cleanly, the whole thing jams. And you have just lost 50% of your power capacity. Instantly. Now, could the mission survive that? Technically, yes. The spacecraft can still function on half power, but it would be a crippled shadow of its former self, a forced diet. You would have to shut down entire science instruments. You would have to choose which experiments get to live and which get to die. Every observation would be a compromise. And for a mission built to answer the biggest question of all, is there life beneath that icy crust? Half the science is a tragedy, so the deployment has to be perfect. And that is just the start of the trouble. Because once those panels are out, they have to stay out. And that is far harder than it sounds. Here is a weird fact about space. Nothing is rigid. We think of spacecraft as solid metal boxes, but in reality they are flimsy, especially when you bolt a 30-metre-long sail onto the side of a bus. Those panels are made of lightweight carbon fibre and thin-film solar cells. They are designed to be light, not strong. They are designed to catch photons, not to resist forces, and Jupiter has forces. As Clipper approaches the giant planet, it will start its gravity-assist manoeuvres and its long, looping orbits. This is where the structural flex problem kicks in. When the spacecraft passes through the strong gravity gradients near Jupiter, the panels will feel a differential pull. The ends of the panels are farther from the planet than the centre, so the gravity tug is uneven. It yanks, it twists, and those massive wings will flex. Engineers have modelled this, they have run the numbers, and the numbers are terrifying. During the most aggressive manoeuvres, the tips of the solar panels can deflect by up to 2 metres. 2 metres! Imagine standing on the wing of an airplane and watching the end of it flop up and down by the height of a tall man. That level of flex creates stress. And if the flex exceeds the design limits, if the structure hits a resonant frequency, or if a joint fatigues, the panel could snap. Just snap off. And then you do not have a half-power problem. You have a dead spacecraft. No power, no heat, no communication. Just an expensive piece of scrap metal drifting around Jupiter. And as if that was not enough, the temperature is playing its own cruel game. Those panels are not just flexing, they are cooking. And freezing. And cooking again. The thermal cycling is brutal. When Clipper is in direct sunlight near Jupiter, the panels can reach 120 degrees Celsius. That is hot enough to fry an egg. But then the spacecraft enters Jupiter's shadow for an eclipse, and within minutes, the temperature plummets to negative 150 degrees Celsius. That is a swing of nearly 300 degrees in minutes. This thermal shock is a silent killer. Different materials expand and contract at different rates. The aluminum frame wants to grow when it gets hot. The Kapton substrate, the plastic film that holds the solar cells, has a different expansion coefficient. Something has to give. And what gives are the solar cells themselves. They develop microcracks, tiny, invisible fractures. Over time, these cracks accumulate. They break the electrical pathways. The power output slowly, inexorably degrades. The engineers designed the panels with a margin for this degradation, but they are essentially fighting a war of attrition. Every orbit, a few more cells die. And the spacecraft has to be smarter about how it uses its remaining power. That is why the battery matters so much. Clipper carries a lithium-ion pack that can store about 40 amp-hours. That is roughly the capacity of a large car battery. Not a massive reserve, but enough to get through a short eclipse or to buffer a high-power radar burst. The problem is that battery cannot stay dead. It has to remain charged. And during the high radiation flybys, when the spacecraft is diving through Jupiter's hellish magnetosphere, the electronics are under constant assault. The battery has to be protected, monitored, and kept warm. If it freezes, it is a brick. If it overheats, it could vent, and you cannot fix a battery in deep space. So the power system is a delicate dance of generation, storage, and consumption, all balanced on a razor's edge. The teams on Earth have spent years testing these panels. They have put them in vacuum chambers. They have shaken them on vibration tables. They have baked them, and frozen them, and flexed them. But there is no way to truly simulate a 30-metre structure in full sunlight at Jupiter distances. There is no way to test for every possible failure mode. You can only do your best and then trust. Trust that the springs will fire. Trust that the hinges will turn. Trust that the cracks will stay small. Trust that the battery will hold. And hope that the universe, for once, decides to cut you a little bit of slack. Because no matter how carefully you design a spacecraft, no matter how many times you run the simulation, you can never truly account for everything. But sometimes the universe throws you a curveball that is less of a threat and more of a temptation. And when it comes to Europa Clipper, That temptation has a name. It is a geyser, a colossal kilometre-high plume of water vapour erupting from the south pole of a frozen moon. We first saw these things back in 2012 and again in 2016. The Hubble Space Telescope, that old workhorse of the cosmos, was staring at Europa when it caught something anomalous. Something that shouldn't really be there. A massive cloud of water vapour, towering 200 kilometres above the surface. To give you some perspective, that is more than 20 times the height of Mount Everest. It is a planetary-scale fountain, and it is spewing directly from the icy crust of a world that we have been dying to touch for decades. Now, let's talk about what these plumes actually are. They are not your classic Yellowstone geyser. This is cryovolcanism. Imagine an ocean deep beneath miles of ice, constantly under immense pressure. That pressure finds a weak point, a crack in the crust, and it forces liquid water out into the vacuum of space. The water instantly flashes into vapour and freezes into tiny ice crystals. The result is this spectacular, violent jet of material that connects the hidden ocean directly to the outside world. And this is where the paradox starts. For a scientist, this is the Holy Grail. We have been talking for decades about how to drill through Europa's ice shell. It would take a massive nuclear-powered probe and years of work to get a few centimetres down. But here, nature has done the drilling for us. The plume is a free sample return. It takes the water from that deep ocean and sprays it into space, making it accessible for any passing spacecraft with the right instruments. It is the dream scenario. You get to taste the chemistry of an alien ocean without ever having to land. But here is the other side of that coin. If these plumes are a scientific goldmine, they are also a potential death sentence for the spacecraft. You have to remember the speed at which Clipper will be moving. For a close flyby, we are talking about a velocity relative to the surface of around 4 kilometers per second. That is insanely fast. If you fly through a plume at that speed, the water vapour and the ice particles are no longer just pretty crystals. They become abrasive projectiles. They become sandpaper moving at hypersonic speeds. Consider the delicate instruments on board. The mapping spectrometer, for example, has incredibly sensitive optics. Its mirrors and lenses are polished to a near-perfect finish. Now, imagine a cloud of microscopic ice particles slamming into that mirror at 4 kilometers a second. It would be like holding a piece of glass under a sandblaster. One close approach through an active plume could literally erode the surface of the optics. It could fog them up, scatter the light, and destroy years of scientific planning in a matter of seconds. It is not just the optics, either. You have the mass spectrometer. This is the thing that actually sucks in particles and analyzes them. It has an intake, a little opening that faces the direction of travel. Now, if you fly through a thick cloud of ice dust, you are not just collecting a pristine sample. You are forcing a high-density flow of solid debris into a very precise, very fragile instrument. You could clog the inlet. You could physically break the internal components. And the worst part is, you might not even know you have damaged it until the next flyby, when the data stops making sense. But the physical damage is only half the story. There is a more immediate, and frankly more terrifying, risk to the spacecraft itself. Attitude control. In the vacuum of space, you control your orientation using tiny thrusters or reaction wheels. You need to know exactly where you are pointing. Now, imagine you fly into a plume. You have a massive, uneven force hitting one side of the spacecraft. That is not a gentle breeze. That is a torrent of vapour and particles slamming into your hull. It will push you off axis. It will create a torque that the onboard computer has to fight against. If that torque is strong enough or unexpected enough, the spacecraft could start tumbling. And a tumbling spacecraft is a dead spacecraft. You lose your antenna lock on Earth. You lose your power generation from the solar arrays. You lose control. So the logical thing to do would be to just avoid the plumes altogether, right? fly a safe orbit, stay away from the South Pole, protect the hardware, that would be the safe choice. It would be the boring choice. But it is not the choice that the mission planners are making. Because this is a scientific mission, and the whole point is to look for signs of habitability. The whole point is to taste that ocean. So, instead of running away from the danger, they are planning to fly straight into it. This is the ultimate high-risk, high-reward maneuver in modern planetary science. The plan is designed for targeted plume sampling. The spacecraft will carry an ultraviolet spectrograph called Europa UVS. Before every single flyby, this instrument will scan the limb of the Moon, looking for the specific ultraviolet glow of water vapour. It will act as the eyes of the spacecraft. If it sees a plume rising from the surface, it triggers an immediate change in the plan. Now, here is where the technology gets truly mind-bending. The spacecraft has an autonomy system. It can make decisions on its own, in real time. Because the signal delay to Jupiter is too long for ground control to react. You cannot call home and say, "Hey, we see a plume, should we go for it?" By the time the message gets to Earth and back, the flyby is over. The spacecraft has to act alone. So, if the UVS camera spots a plume, the onboard computer says, "Target acquired." It then adjusts the spacecraft's attitude. It physically rotates the entire probe so that the open inlet of the mass spectrometer is facing directly into the stream of the plume. It sacrifices the safe orientation. It accepts the risk of abrasion. It accepts the risk of tumbling. And for a handful of precious seconds, as it screams through that column of vapour at 4 kilometers per second, it sucks in a sample of the ocean. It is a terrifyingly beautiful concept. The spacecraft becomes a hunter. It sees the prey, and it pivots to strike. The potential reward is almost immeasurable. You could identify organic molecules. You could find amino acids. You could find direct evidence of chemical disequilibrium, which is the hallmark of a living system. You might be tasting the signature of life for the very first time. But the risk remains. What if the instrument is wrong? Think about the false positives. Europa is a dynamic world. There are dust clouds kicked up by micrometeorite impacts. There are transient thermal events. There could be other forms of outgassing that look like a water plume, but are actually something else entirely. The autonomy system has to be perfect, and it has to be fast. If it misidentifies a dust cloud as a plume, it will waste the flyby. It will waste the science. It will point the mass spectrometer into a cloud of sterile rock dust instead of the life-giving water. You do not get that flyby back. You have to wait weeks or months for the next one. So, we are left with a situation that perfectly captures the tension of this entire mission. We are sending a robot to one of the most hostile environments in the solar system, specifically to chase one of the most dangerous things it could encounter. We are asking it to bet everything on a split-second decision. The plumes represent the shortest path to the answer we are seeking. But they also represent the fastest way to end the mission. The universe is offering us a direct sample of an ocean, but it is hiding that sample inside a sand blaster, and the success of the entire endeavour might come down to whether the software trusts the data enough to pull the trigger. The spacecraft has survived the radiation, threaded the needle through the gas torus, and successfully pulled off a daring flyby. It has gathered data on the plume, if one was there, and it has taken stunning images of the fractured ice below. But now the Clipper faces a different kind of enemy. Not a physical one, like a high-speed dust grain, but an invisible, omnipresent force, Jupiter's magnetic field, and within that field we are trying to read a ghost. Think about what we are trying to do here. We are sending a machine 1 billion miles from home. We are asking that machine to hover near a moon being constantly battered by the most intense magnetic and radiation environment in the solar system, outside of the sun itself. And on top of all that, we want it to detect a signal that is 20,000 times weaker than the noise it is swimming in. It is a little like trying to hear a whisper from across a crowded stadium during a rock concert. But the whisper, in this case, is the very thing we came to find. The ocean's magnetic signature. Let's break this down. Europa's hidden ocean is not pure water. It is salty. Very salty. Think of the Dead Sea, but on a planetary scale. This salinity makes the ocean conductive. It is basically a giant liquid battery wrapped inside a shell of ice. Now, as this liquid battery orbits Jupiter, it moves through that planet's monstrous magnetic field. And because of the laws of physics, this movement induces a secondary magnetic field. It is a response. Europa's ocean essentially pushes back against Jupiter's field. It creates its own faint fluctuating magnetic bubble, and this induced field is the scientific goldmine. If we can measure it accurately, we can tell you not only that the ocean exists, but how deep it is, how salty it is, and even how the ocean circulates beneath the ice. It is the most direct way to read the ocean's signature. But here is the problem. Jupiter's background magnetic field is enormous. It is the strongest of any planet in the solar system. It is roughly 20,000 times stronger than the little induced field we are looking for. That is like trying to measure the light from a single candle from 50 miles away while standing in direct sunlight. And to make matters worse, Jupiter's field is not static. It wobbles. It pulses. It changes with latitude, longitude, and time. It is a chaotic beast. The Clipper's magnetometer has to somehow separate the ocean's quiet whisper from this Jovian roar. So, how do you build a machine that can do that? First, you need the right tool. The Clipper carries a fluxgate magnetometer. It is a classic design, proven over decades of space exploration, but it is exquisitely sensitive. However, a sensitive instrument is useless if it is sitting right next to a noisy spacecraft. And make no mistake, the spacecraft is noisy. Every time a heater turns on, it generates a small magnetic field. Every time a reaction wheel spins up, it creates a disturbance. The power converters, data processors, radios, every piece of electronics is a tiny magnetic contaminant. If you place the magnetometer on the main body of the Clipper, the spacecraft's own magnetic field would completely swamp the ocean signal. You would be measuring the noise of your own machine, not the whispers of Europa. So, the engineers did something clever. They put the magnetometer on a boom, a very long boom, 9 meters long. That is about the length of a standard pickup truck. This boom deploys after launch, extending the sensor far away from the main body. The idea is simple. Distance equals isolation. The magnetic field strength drops off with the cube of the distance. So, by moving the sensor just a few meters away, the spacecraft's magnetic contamination is reduced to a faint background hum. But even that is not enough. This is where the concept of magnetic cleanliness comes in. It sounds like a joke, but it is one of the most serious parts of the entire mission. Every single component that goes into the Europa Clipper is tested before installation. Engineers place each part inside a special magnetically shielded room called a magnetically clean facility. They spin the component, test it in different orientations, and measure its magnetic moment. It is a bit like a police lineup for electronics. Any part that has a strong, permanent magnetic field is rejected. It gets sent back to the manufacturer for redesign. This process took years, and the wiring on the spacecraft is a masterpiece of careful engineering. Standard wiring can act like an antenna for magnetic noise. So, the Clipper uses twisted pairs of wires. By twisting the positive and negative wires together, the magnetic fields from the current cancel each other out. The roots are also designed to have low inductance, meaning the wires are kept as short and direct as possible to minimize unwanted magnetic loops. Every decision, from the type of solder to the orientation of a single screw, was made with the magnetic field in mind. But even with the boom and the cleanliness campaign, there is still a residual magnetic field from the spacecraft. It cannot be eliminated entirely, so the engineers must calibrate it. Before the Clipper ever gets close to Europa, it will perform a series of calibration maneuvers in deep space. It will spin the spacecraft, roll it, and compare the readings from the magnetometer on the boom with readings from a less sensitive backup sensor on the main body. By carefully mapping how the spacecraft's own field changes with orientation, they can build a digital filter that subtracts that noise from the data. It is like having a noise-cancelling microphone for magnetism. Now let's talk about the science of the readout. When the Clipper swoops past Europa, the magnetometer will record the total magnetic field at that point. But the data is not a simple number. It is a waveform. It is a curve that changes over time. The induced field from the ocean has a very specific signature. It does not perfectly align with Jupiter's rotating field. It lags behind. It is out of phase. The angle of this lag is determined by two things: the electrical conductivity of the ocean, which is controlled by salinity, and the depth of the water layer. A thick, highly saline ocean, like our own earthly oceans, will produce a strong, clear phase lag. It will be a loud signal. You will see it clearly in the data on the first flyby. But if the ocean is thin, only a few kilometers deep, or if the water is surprisingly fresh, then the induced field is weak. It is quiet. It could be so faint that it gets lost in the residual noise from the spacecraft or the fluctuations in Jupiter's own field. That is the nightmare scenario for the science team. They have spent years preparing for this, but they know the universe does not owe us an easy answer. This is not a guaranteed detection. It is a gamble. The Clipper will perform multiple flybys. Each flyby will happen at a different longitude over Europa, meaning the Moon will be oriented differently relative to Jupiter's magnetic field with each pass. By stacking these measurements, scientists can build a three-dimensional model of the subsurface electrical structure. They are not just looking for a yes or no on the ocean. They are trying to map its anatomy. They want to know where the water is thickest, where it is most conductive, and where there might be upwellings or currents. It is a tomographic scan of an alien world done entirely through magnetic fields. So, the success of the mission does not just come down to surviving the radiation or dodging the plumes. It comes down to whether this incredibly sensitive instrument, isolated on its 9-meter boom, can pull a whisper out of a hurricane. It comes down to whether the software on Earth can sift through millions of data points and find that one phase lag. It is a test of our engineering, patience, and physics. Because that phase lag, that tiny delay in the magnetic field, is the closest thing we will ever have to a direct handshake with the ocean of Europa. And if we can read it, we will have done something remarkable. We will have proven that the largest ocean in the solar system is not just a theory. It is a real, tangible, observable place. But here is the problem. The Clipper is about to cross 1,500 million kilometers of empty space to get there, and the moment it arrives, the first thing it will have to do is learn how to fly completely alone. Because once that spacecraft swings into orbit around Jupiter, it will be plunged into darkness. Not the darkness of space, the darkness of silence. A radio blackout that will last for hours at a time. And during those hours, no one on Earth will have any idea what is happening. No one will be able to help. No one will be able to fix a mistake. The Europa Clipper will be the most isolated object humanity has ever sent to another world, and it will have to survive on its own. Let me walk you through the geometry of this situation, because it is honestly kind of terrifying when you stop and think about it. Jupiter is big. That is an understatement. Jupiter is the largest planet in the solar system, and its gravitational field dominates everything around it. But from the perspective of a radio signal, Jupiter is also a solid wall. The planet itself, its atmosphere, its radiation belts, they all block radio waves like a concrete wall, blocks a flashlight beam. So when the Clipper swings around the far side of Jupiter on its 21-day orbit, there will be a period lasting anywhere from 4 to 6 hours where the spacecraft simply disappears. It will be behind the planet. The Earth will be on the other side. And there will be no signal. None. Zero. The Clipper will be flying blind, and we will be waiting blind. And the only thing that will matter is the software. Now, this is not a one-time event. The Clipper is scheduled to perform over 40 orbits during its science phase. That means over 40 occultation events, each one of them a 4 to 6 hour blackout. Do the math. That is easily 200 hours of total radio silence across the mission. 200 hours where the spacecraft has to make its own decisions. 200 hours where any mistake, any glitch, any stray cosmic ray that flips a bit in the wrong direction could trigger a cascade failure that ends the mission before it even really begins. And the worst part is, we will not even know it happened until 21 days later. But the occultation is only part of the problem. There is another obstacle out there, and it is something that most people have never even heard of. It is called the Io plasma torus. Imagine a donut, a giant invisible donut made of ionized gas, wrapped around Jupiter. This donut is created by the volcanic hellscape of Io, the innermost of the 4 large moons. Io is the most volcanically active body in the solar system, and it spews sulfur and oxygen into space like a geyser on steroids. Those particles get ionized by Jupiter's magnetic field, and they form a ring of charged plasma that stretches all the way out to Europa's orbit. And here is the kicker. That plasma absorbs radio signals. It scatters them. It distorts them. When the Clipper passes through that donut, the signal becomes a garbled mess. Sometimes it disappears entirely. So even when the spacecraft is not behind Jupiter, it might still be invisible. The engineers at JPL spent years designing the communication system for this mission. The Clipper uses a K-band radio system, which is essentially a very high-frequency microwave link. It is incredibly efficient, capable of transmitting huge amounts of data at high speeds. But it is also extremely directional. The spacecraft carries a 3-meter high-gain antenna, a dish that looks like a dinner plate made of gold. That dish has to be pointed directly at Earth with incredible precision. If it is off by even a fraction of a degree, the signal is lost. And during the plasma torus crossings, the signal attenuation is so severe that the dish might as well be pointed at a wall. So how do you solve a problem like this? You cannot. You cannot control a spacecraft that is out of range. So instead, you teach it to control itself. This is where the autonomy software comes in. Before each orbit, the mission team uploads a set of command sequences. These are not general instructions. They are specific, step-by-step orders covering every single action the spacecraft will take for the next 21 days. Every thruster burn, every instrument activation, every science observation, every data download, everything. The spacecraft executes these sequences like a piano player following a sheet of music. But if the music changes, if something unexpected happens, the piano player has to improvise. And that is the part that keeps engineers awake at night. Because space is not a predictable place. Cosmic rays hit the electronics. Temperature fluctuations cause materials to expand and contract. Radiation causes bit flips, where a 0 turns into a 1 or a 1 turns into a 0. If that bit flip happens in the wrong part of the software, it could tell the Clipper that the antenna is malfunctioning, or that the engine is overheating, or that the spacecraft is tumbling out of control. And if the fault protection software detects that kind of anomaly, it will do exactly what it was programmed to do. It will stop everything and go into safe mode. Safe mode is the spacecraft's last resort. It is a pre-programmed state that does only one thing. Point the solar panels at the sun, switch to backup systems and wait. It is a safe harbour, a place where the spacecraft can sit quietly until the signal reaches Earth, and the team can diagnose the problem. But safe mode comes at a terrible cost. Because when the spacecraft is in safe mode, it is not doing science. It is not collecting data. It is not taking pictures of Europa. It is just sitting there, waiting. And if the spacecraft goes into safe mode during a critical flyby when it is skimming just 25 kilometers above the surface of Europa, that flyby is lost. The entire encounter, the hours of planning, the months of orbital mechanics, the years of design, all of it evaporates in an instant, and you cannot get it back. The Clipper only gets so many flybys. If you lose one, you lose the data from that one forever. So the engineers had to tune the fault protection thresholds. Too sensitive, and the spacecraft will abort perfectly good flybys because of a false alarm. Not sensitive enough, and a real problem could destroy the spacecraft before the software even notices. It is a balancing act. A tightrope walk between caution and courage. And the biggest threat is the false positive, a radiation-induced bit flip that makes the spacecraft think it is dying when it is not. A software glitch that reads a sensor reading wrong and triggers a shutdown. These events are rare, but they happen, and when they happen during a blackout, the Clipper is already gone. It has already made the decision. And all we can do is wait 21 days for the next communications window. Speaking of communications windows, that is another nightmare entirely. The Clipper cannot just talk to Earth whenever it wants. Radio signals take time. At the distance of Jupiter, a signal takes between 35 and 52 minutes to travel one way. That means a round-trip message takes over an hour. You cannot have a conversation. You cannot ask a question and get an answer in real time. So the mission team schedules communication windows months in advance, using the Deep Space Network, a global array of antennas in California, Spain and Australia. Each window lasts about 8 hours to download data, upload new commands, and check the health of the spacecraft. If the Clipper misses that window, for any reason, it has to wait for the next one. And the next one does not come in a day or a week. It comes in 21 days. 21 days of silence. 21 days of wandering. 21 days where the spacecraft is flying alone in the dark. So when the Europa Clipper swings behind Jupiter for the first time, and the signal fades from the control room monitors, and the engineers sit in silence, staring at static, they will know exactly what is happening. They will know that the most expensive, most complex, most ambitious mission ever sent to the outer solar system is now operating completely on its own. They will have done everything they can. They will have written the command sequences. They will have tuned the thresholds. They will have tested the fault protection 1,000 times. And now, all they can do is wait. Wait for the signal to come back. Wait for the spacecraft to emerge from behind that giant, silent wall. Wait to find out if their piano player managed to survive the concert without a conductor. And so the piano player has made its first move. But now it has to face the music. And the music of Jupiter is not a symphony. It is a scream. It is a howling, invisible storm of energy. And before we even get to the radiation, there is the cold. A cold so profound, so absolute, that it can shatter metal and turn fuel into stone. We are talking about the thermal environment of Europa. It is a place where the sun is a distant, unhelpful pinprick of light. The surface of that icy moon averages a staggering negative 160 degrees Celsius. That is not just cold, that is cryogenic. That is the temperature of liquid nitrogen. If you were to step onto that surface without a suit, your blood would freeze in your veins before you could blink. Your eyeballs would turn to ice. Your lungs would crystallize. The human body is built for a very narrow band of temperatures. Europa is the exact opposite of that band. Now think about the Europa Clipper. It is a machine built for that hell. But here is the crazy part. Inside that machine there is a vault, a shielded room, wrapped in layers of lead and titanium, and inside that vault the electronics need to stay at a balmy 20 degrees Celsius. That is room temperature. So, on the outside, the spacecraft is facing negative 160. On the inside, it has to be a cosy, air-conditioned office. This is not a minor challenge. This is an engineering nightmare. Because when the Clipper swings by Europa, the instruments on the outside are exposed to that cryogenic vacuum. They are not built to stay warm. They are built to survive the cold. But they cannot survive it for long. They freeze solid in seconds. So the spacecraft has to be a kind of thermos, a very, very smart thermos. The first line of defense is the multi-layer insulation blankets. These are not your grandmother's picnic blankets. They are technical marvels. The entire spacecraft is covered in them, layer upon layer of thin, reflective material. Think of it like a stack of 100 ultra-thin, shiny space blankets. We are talking up to 30 layers thick. Each layer reflects infrared heat back towards the vault. It is like wrapping a hot potato in a dozen layers of aluminum foil. The heat wants to escape into the cold void, but the blankets keep bouncing it back. They are the first wall against the freeze, but they are not enough. You cannot just trap heat. You have to generate it. And that is where the heaters come in. These are small, electric heaters powered by the massive solar arrays. They are dotted all around the vault, keeping the electronics warm. But here is where it gets sneaky. The heaters are not running all the time. They are on a smart grid. They cycle on and off, like a thermostat in your house. But the danger is not just the constant cold. The real danger is the thermal cycling. That is the killer. Every single flyby of Europa is a dramatic temperature swing. The Clipper comes in from the dark, cold space of Jupiter's shadow. Then it swings out into the full unfiltered glare of the sun. This happens in minutes, not hours. Minutes. Imagine taking a glass vase from your freezer and putting it directly into a roaring fireplace. That is what we are doing to this spacecraft, over and over again. The metal structure of the solar panels expands when it gets hot and contracts when it gets cold. It shrinks and grows with every single orbit. The multi-layer insulation blankets are not exempt. They crinkle and buckle. They are like old parchment, flexing and creasing. But the most terrifying part of this thermal dance is the propellant lines. The Clipper carries hydrazine fuel for its thrusters. It is a volatile, energetic chemical. It is also a liquid that freezes at a surprisingly high temperature, just -2 degrees Celsius. That is barely below the freezing point of water. If the fuel lines drop below that temperature, the hydrazine turns into a solid. It becomes a lump of chemical ice inside the pipe, and if that happens, the thrusters cannot fire. The spacecraft loses its ability to steer. It cannot adjust its trajectory, and you cannot simply thaw it out in space. The whole mission would be lost. So the fuel lines have to be actively heated. They are wrapped in their own dedicated heaters and thermostats. A small army of warmth, fighting off the eternal freeze. But even the heaters are not the most clever part of the system. To truly navigate this thermal hell, the Clipper uses a technology you might find in a high-end gaming laptop. Heat pipes. These are not your average pipes. They are sealed tubes, embedded in the walls of the radiation vault. Inside each tube is a small amount of a working fluid, in this case, ammonia. When the electronics inside the vault start to heat up, that heat travels to the hot end of the pipe. The ammonia absorbs that heat and boils. It turns into a vapor. That vapor, now under pressure, travels to the cold end of the pipe. The cold end is connected to a radiator that faces the cold of space. There the vapor releases its heat, turns back into a liquid, and the cycle starts all over again. It is a passive, self-regulating cooling system. It is brilliant. It is elegant. It is also terrifyingly fragile, because if a single heat pipe fails, the whole systems can spiral out of control. A micrometeorite impact, a tiny manufacturing defect, a hairline crack that you could not see on Earth. If that pipe fails, the heat has nowhere to go. The electronics inside the vault will start to cook. They will overheat, they will shut down, and a silent, dead spacecraft will drift past Europa, a tombstone in the void. This is why the thermal design philosophy is so paranoid. Every single component, every screw, every wire, every sensor is assessed, for its minimum and maximum operational temperature. What temperature does it need to survive? What temperature will kill it? The instruments that have to face outward, like the cameras and the spectrometers, are a special case. They have to be pointed at the cold sky. They have to look at Europa's icy surface. They cannot hide under the blankets. So they are equipped with their own tiny heaters. These heaters are not running all the time. That would waste too much power. They are only activated during the flyby. For the few minutes when the instrument is staring into the cold, those heaters flick on. They keep the lens and the sensor from frosting over. They stop the delicate optics from shattering. It is a game of seconds, a race between the cold and the warmth, and the engineers have to calculate exactly how long those instruments can survive without that heat. It is a constant, silent negotiation with the environment, a delicate balance between boiling and freezing, between life and death, and at every single step the spacecraft is fighting, not against a monster, not against a storm, but against the simple, inevitable, crushing cold of space. And so, as Europa Clipper sails into the deep void, it carries with it more than just the hopes of a billion-dollar science mission. It carries the ghosts of those who came before. Every spacecraft that has dared to cross the solar system and attempt something this audacious has left behind a trail of scars. Lessons written in failure, in hardware that jammed, in software that forgot its purpose at the worst possible moment. And if we want to understand the biggest danger Clipper will face when it reaches Jupiter, we have to look back at one mission in particular. A mission that was supposed to be the jewel of NASA's deep space fleet. A mission that nearly became a silent, drifting tomb of lost data. I'm talking about Galileo, NASA's previous grand tour of Jupiter. Launched in 1989, it arrived in 1995 after a long, winding journey through the inner solar system, and it was, by any measure, an engineering marvel. A spacecraft built to withstand the most punishing radiation environment we had ever encountered. But here's the thing about engineering marvels. They are still made by human hands. And human hands make mistakes. Galileo's great tragedy was not a failure of the science or the navigation. It was a failure of a single piece of mechanical hardware. Its main high-gain antenna. The thing that was supposed to be the spacecraft's voice, screaming back to Earth at 134,000 bits per second. That antenna had to unfurl like an umbrella, a delicate, precisely timed dance of ribs and mesh, and it jammed. A few tiny ribs got stuck. Just a few, and suddenly that screaming voice was reduced to a whisper. Not 134,000 bits per second. 10 bits per second. That is a reduction in data transmission by a factor of 10,000. Think about that for a second. You're trying to send back pictures of Jupiter's moons, of volcanic eruptions on Io, of the icy crust of Europa, and you can only dribble that data back home at the speed of a dial-up modem from the 1990s. Galileo had to rely on its low-gain antenna, a backup system meant for emergencies only, and it spent years slowly trickling the data home. The entire mission was saved by sheer grit and clever engineering, but it was a constant, agonizing battle against the clock, and here is the terrifying part for Europa Clipper. It has no such backup for its antenna. Its main high-gain antenna must deploy perfectly. The mechanism has been tested, retested, and tested again. But space is the ultimate test. And in that cold, silent blackness, a single stuck rib could turn Clipper from a revolutionary explorer into a very expensive piece of space junk. But Galileo's ghost is not the only one whispering warnings in the ears of the mission engineers. Look at Cassini, Saturn's beloved explorer. A mission that was nearly flawless for over a decade. But even Cassini had its moments of sheer terror. During its tour of the ringed planet, the spacecraft experienced multiple safe mode events. Safe mode is the spacecraft's way of saying, I am scared. I do not know what is happening. Stop everything. Point my solar panels at the sun, and wait for instructions from the ground. That sounds reasonable. Until you realise that during a critical flyby of Titan, when Cassini was supposed to be gathering the most precious data of its entire mission, the computer decided it was time for a nap. It entered safe mode, and the entire flyby was lost, all that data, gone, because a software glitch or a cosmic ray hit a sensitive circuit at the worst possible moment. Cassini recovered. It carried on. But the lesson is seared into the minds of every mission planner. You can do everything right. You can test the hardware for years. And then, in the space of a few milliseconds, one stray particle can turn your masterpiece into a dumb, frightened brick. Or consider the Mars Reconnaissance Orbiter, a mission designed to map the red planet in stunning detail. It was performing an error-braking maneuver, dipping into the thin Martian atmosphere to slow itself down. A delicate, dangerous dance. And then, a software bug. A simple error in the code, and the spacecraft slammed into safe mode in the middle of that maneuver. The team on Earth had to scramble, literally working around the clock, to bring it back before it either skipped out of the atmosphere or burned up entirely. They saved it, but the scare was real. It was a reminder that the software running these billion-dollar machines is written by human beings, and human beings make typos. They forget a semicolon. They misjudge a margin. And in space, a typo can cost you everything. And let's not forget Kepler, the planet hunter. A mission that revolutionized our understanding of the galaxy. It depended on reaction wheels to stay perfectly pointed at a tiny patch of sky. Reaction wheels are spinning flywheels that let the spacecraft turn without using fuel. They are beautiful, simple, and utterly critical. Kepler lost its first reaction wheel. The team adapted. It lost its second, and the primary mission ended. It was a mechanical death. The bearings simply wore out. Now, Europa Clipper has 4 reaction wheels. 3 are used for control, and 1 is held as a cold spare, sitting idle, waiting for the day it might be called into duty. And the engineers know, with a grim certainty, that radiation at Jupiter will wear those bearings down. It is not a question of if a wheel will fail. It is a question of when. If 1 wheel fails, the spacecraft can still operate on 3. That is the designed margin. But if a second wheel fails, things get ugly. Really ugly. Because then, the spacecraft must switch to thruster-only control. Those 24 small thrusters that are normally used for fine adjustments will suddenly have to do all the work. And they drink fuel. The hydrazine propellant is a finite resource. Once you start using thrusters for attitude control, you are on a clock. A ticking clock that counts down to the end of the mission. The team has planned for this scenario. They have written the commands. They have rehearsed the procedures. But it is a plan for survival, not for thriving. Every second of thruster use is a second closer to the fuel gauge hitting empty. And behind all of this hardware, all of these redundant systems, all of this planning, there is the human factor. And this is where the biggest danger really starts to become clear. The Europa Clipper mission team has over 100 engineers, on call 24 hours a day, 7 days a week during critical phases. These are people who have dedicated years of their lives to this single spacecraft. They know its quirks. They know its weaknesses. They have run simulations of every possible failure mode they could imagine. But they cannot imagine everything. When an anomaly happens, the protocol is something called mission assurance. It is a system of checks and balances so rigorous that it can feel almost paranoid. No command is ever sent to the spacecraft without multiple independent checks. 3 people have to sign off, sometimes 4. The logic is simple. A single person's mistake, a single typo in a command string, could kill the mission. So you build a wall of verification around every single keystroke. But here is the nightmare, the communication delay. When Clipper is at Jupiter, a radio signal travelling at the speed of light takes between 35 and 50 minutes to get from the spacecraft to Earth. Then, the engineers have to analyse the data, decide what to do, and send a command back. That is another 35 to 50 minutes. So an anomaly happens. The spacecraft detects a problem. It goes into safe mode. It waits. 90 minutes later, the team on Earth knows something is wrong. They spend hours, sometimes days, figuring out the root cause. Then they craft a solution. Then they check it. Then they check it again. Then they send it. And 90 minutes later, the spacecraft receives the command. By then, the situation might have changed. The spacecraft might have drifted. The temperature might have dropped. The power might be draining. So the decisions, the most critical decisions of the entire mission, have to be made in advance. The team writes what are called fault protection rules. They program the spacecraft to react autonomously, to make life or death choices without waiting for a human to say yes. It is a terrifying responsibility. You are essentially teaching a machine to be afraid, to prioritize survival over science, to make a call that a human would normally agonize over for a week, and you have to get it right the first time. Because out there in that crushing cold, there is no second opinion. There is only the ghost of Galileo whispering a warning about the things that jam, and the ghost of Cassini reminding you that even the best computers can have a bad day, and the ghost of Kepler showing you that sometimes the only thing between a mission and its end is a worn-out bearing. Clipper fights that battle every day, every hour, every single second. But there is another ghost, one that does not haunt the engineers in the control room, but haunts the biologists, the geologists, the ones who dream of finding something, anything, alive in that dark, saltwater ocean beneath Europa's cracked ice shell. This ghost is not a radiation spike. It is not a stuck valve or a failing thruster. This ghost is us, our own bacteria, our own microscopic hitchhikers, and the terrifying possibility that, in our haste to explore a new world, we might accidentally destroy it before we even get a chance to understand it. Let me explain something that keeps planetary scientists up at night. When we send a spacecraft to Mars, we are fairly confident that any Earth microbes that might survive the journey would die quickly in that thin, cold, radiation-blasted environment. Mars is harsh, it is unforgiving. But Europa is different. Europa is warm. Well, relatively warm. Under that miles-thick ice shell, there is liquid water. There is a global ocean. There are hydrothermal vents on the seafloor, spewing energy and minerals. And most chillingly of all, there is a chemical energy gradient, a constant source of food for any organism smart enough to use it. In short, Europa is a paradise for life, and a paradise is extremely vulnerable to contamination. In the world of planetary protection, Europa is not just a pretty target, it is a monster. It is classified as a Category 3 body. That is not a casual label. It is the most stringent classification for any target we have ever considered, even more restrictive than the rules for Mars. Why? Because the potential for life is so high, and the consequences of contamination are so absolute. Think of it like this. You have just discovered a pristine, untouched rainforest. You want to study it, to catalogue every unique species, to understand its ecosystem. But you have to send in a team of explorers. And those explorers are covered in invasive species. They are carrying seeds on their boots, fungus on their gloves, and bacteria in their lungs. If you are not incredibly, painfully careful, you will not be studying the rainforest anymore. You will be studying the wreckage of it, overrun by your own filth. That is the nightmare scenario for Europa Clipper. So NASA has a rule book, and it is not a suggestion, it is written in fire. The specific rule is brutal. The total number of viable spores on the entire Clipper spacecraft, every single nook and cranny, must be less than 300,000. A single human hand, just one hand, without washing, can carry anywhere from 10,000 to 1,000,000 bacterial spores. That means the entire billion-dollar, multi-ton spacecraft is allowed to be only about as clean as a single pair of clean hands. Maybe even less than that. How do you achieve that level of cleanliness? You do not just wipe it down with a Clorox wipe. You build the spacecraft inside a Class 10,000 cleanroom. That means in every cubic foot of air in that room, there are fewer than 10,000 particles larger than half a micron. For comparison, the air in your living room probably has millions of particles in that same space. The engineers wore full bunny suits, hoods, gloves, and masks. They taped their gloves to their sleeves. They shuffled their feet on sticky mats. Every single tool was sterilized. Every surface was wiped with alcohol. But that was not enough. It was never enough. For the parts that could take the heat, they baked them. I mean, they really baked them. At 125 degrees Celsius for hours. This is not like drying a dish in the oven. This is a brutal, dry, relentless heat that cooks the DNA of any living organism until it is just carbon dust. But here is the problem. Some parts of Clipper absolutely cannot be baked. The propulsion system, for example, is full of delicate valves, seals and pressure regulators that would melt or crack under that heat. The thermal blankets, those shimmering gold and silver layers that protect the spacecraft from the cold of space, are made of materials that would degrade. These sensitive areas were treated with vaporized hydrogen peroxide, a powerful sterilant that breaks down into harmless water and oxygen. Then they were wiped down with ethanol. The technicians called it the spaghetti treatment. They had to painstakingly clean every inch of the plumbing, every hidden crevice, every thread of the bolts by hand. But here is where the story gets truly terrifying. All that cleaning, all those years of effort, all that obsessive attention to detail can be undone in a single moment. If Clipper makes a mistake, a navigational error, a trajectory calculation that is off by just a fraction of a percent. If the spacecraft drifts off course and, instead of safely flying past Europa or going into a stable orbit around Jupiter, it crashes into that ice shell. If that happens, it is a biological disaster. The spacecraft would impact at tens of thousands of miles per hour. It would not just break apart, it would vaporize. But some of that debris, some of that sterile by space standards debris, would survive. And it would be deposited directly onto the surface of Europa, and with it those 300,000 spores. Those spores are tough. They are called spores for a reason. They can survive the vacuum of space. They can survive ultraviolet radiation. And if they land on an area where the ice is thin, or where tidal forces have cracked the shell, some of that debris could potentially reach the ocean. It only takes one single bacterial spore to land in that perfect environment, to find that warm, wet, chemically rich soup, and to start dividing. One spore becomes two become four become 8. In a few weeks, the entire ocean could be contaminated, and we would never, ever know what was originally there. That native life, that potential alien biology, would be gone, replaced by our own terrestrial stowaways. The science would be ruined for generations. That is why there is a very specific job at NASA. It is not a glamorous job. It is not a job that gets you on the cover of a magazine. But it is arguably the most important job in the entire mission. It is the Planetary Protection Officer. Their job is simple, but terrifying. Monitor the trajectory, constantly. Every single day, every week, every month of the mission, this person watches Clipper's path. They run the numbers. They check the gravitational perturbations from Jupiter's moons. They calculate the tiny, almost imperceptible nudges from solar radiation pressure. And they make sure that the probability of Clipper ever impacting Europa remains below 1 in 10,000 over the entire mission lifetime. 1 in 10,000. That is the line. If that probability ever creeps higher, the mission stops. They would have to change the plan. They would have to burn fuel, burn precious propellant, just to steer Clipper away from the very old world it was sent to study. It is a heartbreaking decision to even contemplate, but it is necessary. Because the alternative is the final, unforgivable contamination of a world that might hold the secrets to life itself. It is the ghost of our own existence, reaching out to silence another before we even hear its whisper. And so, after all of that, after the radiation that could cook a spacecraft alive, after the gravitational chaos of the Jovian system, after the risk of being torn apart by plumes or slammed by micrometeoroids. After years of travel and the gut-wrenching anxiety of a slingshot maneuver around a moon that seems determined to destroy anything that gets too close. After all of that, what does Europa Clipper actually find? That is the question that keeps planetary scientists awake at night. That is the ultimate payoff. And let me tell you, the answers are going to be worth every single volt of radiation the spacecraft has to endure. If the Clipper survives, it has the potential to rewrite everything we think we know about the possibility of life beyond Earth. But it is not going to hand us a photograph of an alien fish. It is not that simple. The data comes in layers, like peeling an onion that has been frozen for 4 billion years. There are 3 broad possibilities, 3 outcomes that could emerge from those 40 flybees, and each one is more profound than the last. The first possibility is the confirmation we have all been waiting for. Proof of a global, salty ocean beneath that cracked, icy crust. We are fairly confident it exists, but confidence is not certainty. The Clipper's magnetometer and radar instruments are designed to measure the conductivity of that subsurface water and map its depth. If they return a clear signal, it will confirm that Europa's ocean is not just a series of isolated pockets or a slushy mush, but a global body of liquid water, sitting in contact with a rocky seafloor. That is the first ingredient for life as we know it. But it gets better. The next piece of the puzzle is chemical energy gradients. On Earth, life thrives around hydrothermal vents, not because of sunlight, but because of chemical reactions between hot, mineral-rich water and cold seawater. If Clipper detects similar energy sources on Europa's seafloor through magnetic anomalies or thermal mapping, we will have the second ingredient. At that point, Europa transitions from a maybe to a prime candidate. It becomes the most compelling real estate in the solar system for a second genesis. The second possible outcome is even more dramatic: the discovery of active geology. We are talking about volcanic vents on the ocean floor, cryovolcanism on the surface, and fractures that are actively opening and closing, connecting the deep ocean to the frozen shell above. The Clipper's infrared spectrometers and high-resolution cameras are looking for thermal hotspots, for fresh ice that has not been hit by radiation, for changes between flybys. Imagine this: you are watching the data come in, and you see a region on the surface that was not there during the previous pass. A dark stain, a new crack, a plume that erupts while the spacecraft is flying overhead. That would be a game changer. It would mean that the ocean is not a static, dead pool. It is a dynamic system. It is churning, mixing, and exchanging materials with the surface. That interaction is the engine that drives biological potential, because it allows nutrients from the surface to reach the depths, and it allows chemical energy from the depths to reach the surface. If Clipper finds active geology, we will know that the conditions for life are not just present, they are active and ongoing. The third possibility, the Holy Grail, is the detection of organic molecules. Now we have to be careful here. Organic molecules are not life. They are the building blocks, the bricks, but not the house. The Clipper is looking for amino acids, lipids, and complex carbon chains in the plume material that erupts from the southern pole. It will fly directly through those plumes, sampling the ice grains and gas. If it finds even simple amino acids, the kind that form the backbone of proteins on Earth, that will be monumental. But if it finds something more complex, something that suggests chains of carbon atoms structured in a way that implies biological activity, well, that is a different conversation entirely. The instruments on Clipper are not designed to detect life directly. They cannot see a cell, but they can detect the chemical fingerprints that life leaves behind. If we find a high concentration of specific organic molecules in the plumes, molecules that are unlikely to have formed through purely geological processes, we will have a smoking gun. Not proof of life, but proof that the conditions are so favourable that the question is no longer if, but when. But here is the brutal reality. Even if the Clipper nails every one of these discoveries, we are not going to get the answers overnight. The data rate from Europa is agonizingly slow. We are talking about 10 to 20 kilobits per second. To put that in perspective, that is slower than a dial-up modem from the 1990s. The full dataset from all 40 flybys, the high-resolution images, the radar maps, the magnetic field measurements, the mass spectrometer readings, it will take years to transmit back to Earth. Years. The first compelling results will arrive within the first year. We will know pretty quickly whether the ocean is there and what the basic chemistry of the plumes looks like. But the fine-grained analysis, the deep radar sounding that maps the ice shell in 3 dimensions, the detailed magnetic field measurements that reveal the ocean's salinity and depth, those will take a decade of careful processing and interpretation. We have to be patient. The universe does not give up its secrets quickly. And then comes the inevitable question, what next? If Clipper finds compelling evidence of a habitable environment, the scientific community will scream for a follow-on mission. A Europa lander, a spacecraft that touches down on the surface, drills through the ice, and sends a probe into the ocean. It sounds like science fiction, and frankly it is. The technical challenges are staggering. The surface of Europa is not nice. It is a jagged landscape of ridges and chaos terrain, with radiation levels that would fry any unprotected electronics in a matter of hours. You would have to shield the lander with lead or water, making it incredibly heavy and expensive. And then there is the drilling problem. The ice shell is estimated to be anywhere from 15 to 25 kilometers thick. That is not a thin layer of frost. That is a mountain of ice. We do not currently have any technology that can drill through that. Not even close. The current concept for a Europa lander is mostly a surface laboratory. It would analyse the ice at the landing site, searching for organic molecules that have been churned up from the ocean below by geological activity. But drilling to the ocean itself, that is a project for the next century, if ever. The Clipper's findings will be the deciding factor. If the data is ambiguous, if the ocean is there but dead, the cost of a lander might never be justified. But if the data screams that life is likely, then the world will find a way to pay for it. This brings us to the philosophical heart of the mission. Look, if Europa harbours life, it almost certainly evolved independently from life on Earth. It would be a separate tree of life, a second Genesis. That is not a minor detail. That is a cosmic revelation. It would mean that life is not a freak accident that happened once and only once in the entire history of the universe. It would mean that life is a natural consequence of planetary evolution. Where there is liquid water, energy, and the right chemistry, life will eventually emerge. It becomes an inevitability, not a miracle. And if that is true on Europa, it is true on 1 million other worlds in our galaxy alone. The implications are staggering. We are not alone, not just because there might be aliens out there, but because we are part of a universal process. The Clipper is not just a science mission, it is a philosophical probe. It is testing the very nature of existence, and that is why we accept the dangers, the radiation that could blind it, the gravity that could tear it apart, the plumes that could contaminate it. That is the price. The price of asking the ultimate question. The price of potentially finding out that the galaxy is teeming with the possibility of life. The Clipper will endure that hellish environment, not because it is easy, but because the answer is worth everything. The ghost of our own existence is reaching out. But this time it is reaching out to listen. And so, after all those years of waiting, of building, of worrying, the moment finally arrives. April 2030. Or maybe a little later, because space has a way of keeping its own schedule. The Europa Clipper has survived the 5.5-year journey. It has slipped into orbit around Jupiter, a feat that required a braking burn so precise it makes threading a needle look like child's play. And now, for the first time, the spacecraft is diving down toward its target. Europa, the icy moon, the ghost in the darkness, the alien ocean we have been dreaming about for decades. The altitude for this first flyby is set at 25 kilometers. That sounds like a lot, I know. But think about it this way. If you were flying a commercial airliner across the Atlantic, 25 kilometers would put you 3 times higher than normal cruising altitude. But for a spacecraft, 25 kilometers is practically scraping the ice. It is reckless. It is deliberate. It is the only way to get the data we need. At this altitude, the radiation environment is beyond anything most spacecraft have ever endured. The Clipper's vault, that protective titanium coffin for the electronics, is already warm from the journey. Not warm like a summer day. Warm like a hot engine block. Warm because the heat from its own systems has nowhere to go in the vacuum, and warm because the particle radiation has already begun to seep into the metal. The components inside are being stressed, and they haven't even started the science yet. Every instrument on board has been calibrated in the weeks leading up to this moment. The ice-penetrating radar is humming with a specific frequency that can punch through miles of frozen water. The spectrometer is ready to read the chemical fingerprint of the surface, like a detective reading a crime scene. The mass spectrometer, that finicky little machine designed to taste the faintest wisps of dust, is primed and waiting. All the command sequences are loaded. The flight computer has rehearsed this flyby 1,000 times in simulation. But simulation is not reality. Reality has a way of throwing curveballs. Then, the communication blackout begins. The spacecraft swings behind Jupiter, not Europa, Jupiter, the giant planet itself. The Clipper's antenna can no longer point toward Earth. There is no signal. There is no way to troubleshoot. There is no way to hit pause. For the first time in this mission's history, the Clipper is truly, completely, terrifyingly alone. It is now executing the flyby on its own, running on a script written years ago by engineers who had to guess what conditions would be like. And those engineers are sitting on Earth, staring at static on their screens, knowing that their creation is flying into a wall of fire without a net. The flyby lasts 10 minutes. 10 minutes, that is it. But those 10 minutes are an eternity of mechanical and electrical chaos. The spacecraft's body is buffeted by the magnetic field. This is not a gentle push. It is a twisting, wrenching force, a phenomenon called magnetic torque. Imagine trying to take a photograph while standing inside a tornado. That is what the Clipper is dealing with. To maintain its aim, the reaction wheels spin up. They whir faster and faster, fighting to keep the instruments pointed exactly at the icy surface below. If the wheels lose that battle, the science data is ruined. If the wheels burn out, the spacecraft might enter safe mode and miss the rest of the flyby. Meanwhile, the radar fires its signal into the ice. The spectrometer takes a spectral reading that will tell us what elements are present. The mass spectrometer opens its tiny valve, hoping to capture a molecule of water vapour that might have erupted from one of Europa's famous plumes. It is a ballet of machines performing at their absolute limit, and in the background, the fault protection software is watching everything. Watching the currents, watching the temperatures, watching the star tracker to confirm the spacecraft knows where it is pointed. If any instrument reports an anomaly, if a voltage spike or an unexpected temperature rise creeps in, that fault protection software has to make a decision within milliseconds. Does it abort the flyby and save the spacecraft, or does it trust the data and keep going? The software is not sentient. It has no emotions, but it was programmed by humans who had to imagine every possible failure. And those humans are holding their breath, thousands of miles away, powerless to intervene. Then, as suddenly as it began, it is over. The spacecraft emerges from Jupiter's shadow. The light returns. The solar panels, if they are still intact, begin to catch the distant sun, and the Clipper re-establishes communication with Earth. But nobody on the ground knows that yet, because here is the cruelest part of this entire operation. the light speed delay. Jupiter is so far away that a radio signal takes about 45 minutes to make the one-way trip. 45 minutes. So the Clipper is already safe, or already doomed, and the mission team is just waiting. They are sitting in their control room, watching the clock, waiting for the first ping of health telemetry to crawl across the screen. When it finally arrives, the tension breaks. The data says, the radiation vault temperature is stable. It did not spike, it did not fail. The solar panels are undamaged. The particles did not short out the circuitry. And the science data. Oh, the science data is safely stored, every bit of it locked away in solid-state memory, ready to be transmitted back to Earth over the coming days. The first flyby is a success. But here is the thing that the mission team knows, that the public might not fully appreciate. The biggest danger was not the flyby itself. The flyby was the climax. The biggest danger was the approach. It was those weeks of orbital insertion and manoeuvring, when the Clipper was swimming through a sea of high-energy electrons, slowly accumulating damage. The radiation does not kill you all at once. It does not strike like lightning. It seeps into the components like water into a crack. It weakens the transistors. It degrades the insulation. It introduces tiny errors that build until one day something stops working. The first flyby was the ultimate test, but the silent killer was the journey. And it passed. It passed because the engineers built a vault that could hold back the storm. It passed because the software was paranoid enough to survive. Relief washes over the control room. Weak smiles, deep breaths. There is still so much ahead. There will be dozens more flybys, each one a gamble. But the first one is special. That is the one where you find out if your dreams were built on solid ground or on sand. And for the Europa Clipper, the ground held. The ghost of our own existence, that fragile spark of curiosity, reached out into the void. And the void listened. And so we arrive at the end of this journey. Not the end of the story, of course. That story is still being written, somewhere out there, in the cold, silent dark between the moons of Jupiter. But the end of our telling of it, for now. We have followed this spacecraft from the spark of an idea, through the grinding years of labour, through the terror of launch. We have imagined it, 300 million miles from home, flinging itself through a field of invisible knives. We have seen it dance with gravity, threading the eye of a needle at 17,000 miles per hour. We have watched as engineers built a fortress out of thin metal and pure hope. Let us be honest with each other for a moment. This is not a story with a guaranteed happy ending. This is not a fairy tale. The Europa Clipper is the most complex, the most expensive, the most audacious planetary mission humanity has ever attempted. It is also, by a wide margin, the most fragile. It is a 1-ton box of electronics, launched from a planet that hates its own existence, aimed at a moon that is actively being cooked by the second most dangerous radiation environment in the solar system. The odds are not cute. The odds are not comforting. The engineers who built this thing did so with their eyes wide open. They did not pretend the danger wasn't real. They did not tell themselves that everything would be fine. They accepted that the spacecraft might fail. They accepted that the radiation might degrade its sensors faster than any model predicted. They accepted that a micrometeorite, a grain of sand moving at 20 miles per second, might punch through a critical wire and blind the spacecraft for good. They accepted that a software bug, a single misplaced zero, might lose a whole flyby. That a glitch in the data handling unit could corrupt an entire pass over a plume. That a power spike from a sun-starved solar array could fry the main computer. They accepted all of it, and they built it anyway. Because the question, the biggest question, the one that haunts every thinking creature on this pale blue dot, is worth the risk. Is there life elsewhere? Not just the possibility of it, not the statistical likelihood, but the actual, breathing, swimming, maybe even thinking, presence of something else, somewhere else right now. That is the question the Clipper is being sent to answer. And if it takes a 1 in 3 chance of catastrophic failure to get that answer, that is a price the engineers were willing to pay. That is a gamble we, as a species, were willing to take. Think about that. Think about the sheer audacity of sending a machine across 500 million kilometers of vacuum, through a radiation belt that would kill a human in minutes, to orbit a moon that doesn't even have an atmosphere worth mentioning, all so it can take pictures of ice and sniff plumes of water vapour. It is insane. It is beautiful. It is terrifying. And it is us. This is what we do. We build fragile things and we send them into the heart of the maelstrom, because we cannot stand not knowing. There is a moment, sometime in your life, when you realise that the most important things you will ever do will be done without any guarantee of success. Certainty is a luxury for the small-minded. The big questions, the ones that make us human, demand that we take a leap. The Europa Clipper is that leap. It is a titanium vault full of dreams, flying through a ring of cosmic radiation, and it is carrying the hopes of 7 billion people who want to know if we are alone. So here is what I want you to do. If this story has moved you, if you felt that twist in your stomach when we talked about the radiation, if you felt that surge of awe when we described the gravity assist, if you have ever looked up at the night sky and wondered what is out there, subscribe to this channel. Subscribe to This Is Space. Because this is not the last mission. This is not the last time we will fling our best and our brightest into the unknown. There are more documentaries to be made, more dangers to face, more questions to ask. And if you want to see what comes next, if you want to see the follow-up, the Europa lander, the mission that would actually touch that alien ocean, then like this video. Let us know you want it. This is not a passive crew. You are part of this journey too. And then picture this. Europa Clipper alone. The great red eye of Jupiter glowering in the background, a swirling hurricane of methane and ammonia bigger than the Earth itself. The dark, scarred face of Europa passing below, its icy crust cracked like an eggshell, hiding an ocean that may or may not hold the answer, and between them a tiny speck of human engineering, a whisper of metal and silicon flying through the storm, protected by nothing but a titanium vault and the ingenuity of a species that refused to stay in its cradle, that refused to stop asking why. It is fragile, it is vulnerable, it is alone, but it is there, and it is trying. And if it survives long enough, if the radiation doesn't eat its memory, if the debris doesn't punch through its heart, if the software doesn't glitch, if the gravity doesn't tear it apart, then the data will come. The answer to the biggest question in science will be waiting in those ones and zeros. All we have to do is keep listening. The price of knowledge is high, but the price of ignorance is higher. And out there, in the dark, a tiny emissary from Earth is paying that price for all of us.